600 million years ago, Earth was an alien world, frozen seas, strange oceans, and the first whispers of complex life. What did our planet truly look like back then? Tonight we'll journey into that forgotten era before animals ruled the land. If you enjoy this calm exploration, please like, subscribe, and share, and tell us in the comments, what part of ancient Earth would you visit if you could? Thank you for being here now. Let's begin. The sun sends a steady stream of light and warmth to Earth 600 million years ago, slightly fainter than the modern star, yet constant enough to anchor the planet's daily and seasonal rhythm. Geometry sets the stage. Earth follows a path that is close to circular, so the average distance from the sun changes only a little through the year, and the length of the year remains essentially the same, because orbital period depends on distance rather than on surface conditions. Slow gravitational tugs among planets tilt and turn this path over spans far longer than a human life, but on the scale of years to centuries the arrangement feels steady. Closest approach and farthest reach differ modestly, so no extreme pulse of solar energy arrives at one season and retreats at another. Instead, a gentle modulation arises from how the orientation of the path lines up with the calendar, and that alignment drifts over tens of thousands of years. Seasons arise from the angle of Earth's spin axis relative to the orbital plane. When one hemisphere leans sunward, the midday sun climbs higher there and traces a longer arc across the sky, lengthening daylight and raising the daily dose of energy, while the opposite hemisphere leans away and experiences shorter days and a lower sun. Half a year later, the roles reverse. The strength of this contrast depends on the tilt itself, which wanders on long cycles, and on the slow precession of the spin axis that shifts the timing of the seasons relative to positions along the orbit. Because the sun is modestly dimmer than in later ages, the average power at Earth's distance is slightly lower. A hydrogen-fusing star brightens gradually as it converts core fuel and rearranges its interior, so the luminous output inches upward over geological time. At the time in view, the difference from today is small, yet real enough to matter when balanced against the heat that the planet sheds back to space. The outer boundary condition is simple: sunlight arrives at the top of the air and must in the long run be matched by outgoing radiation if surface temperature is to remain in a broad band. How that balance is achieved belongs to inner layers of this story, but the supply side begins here with the star and the orbit. Daily change is tied to the march of the day-night boundary around the sphere. Where the sun climbs high, the path across the sky nears overhead and lingers for many hours, and the surface absorbs a larger portion of the incoming light. Toward the poles, the arc falls lower, the day shortens outside of summer, and the same energy spreads across a slanted beam. No place receives the same share at all times. At the equator, the cadence is nearly even across the year, with day length close to half the cycle in light and half in darkness. And the midday sun remains high, so the daily intake stays relatively steady. Mid-latitudes see a broader swing with long, bright days and short nights in one season, and the reverse in the opposite season. Near the poles, the year divides into long intervals of low sun and darkness, and shorter intervals of high sun and continuous daylight. Over longer intervals, slow orbital cycles adjust how and where the sunlight falls. A small change in path shape called eccentricity alters the difference between closest and farthest distance. A change in tilt called obliquity alters how far the seasonal sun migrates toward the poles. A change in the direction of the spin axis called precession shifts the timing of the seasons relative to the dates of closest and farthest approach. When closest approach aligns with a hemisphere's summer, that hemisphere receives a slightly stronger summer and a slightly milder winter, while the opposite hemisphere receives the reverse. When tilt grows larger, both hemispheres experience stronger seasons, and when tilt lessens, seasons soften. These adjustments unfold gradually and imprint rhythms that are long compared with a human life, and short compared with deep time. The spectral character of sunlight remains that of a star like the present sun, rich in visible wavelengths bracketed by near-infrared and near-ultraviolet bands. Shorter wavelengths carry more energy per photon and interact strongly with gases and small particles, while longer wavelengths carry energy that warms surfaces and after absorption returns outward as heat with much longer characteristic wavelengths. From the vantage at the top of the air, almost all of the power that drives physical and biological processes originates in this downwelling stream. Its partition across wavelengths matters because different wavelengths are scattered and absorbed in different ways, but the key outer fact is that the sun provides a broad, stable spectrum with minor variability superimposed. Solar variability on scales of days to decades exists, yet the amplitude is small compared with the total. Dark spots and bright regions slightly adjust the output, and cycles alter the count of these features. Streams of charged particles sometimes rush outward, but the energy content of these bursts is minor compared with the persistent radiance. Against that steady backdrop, the planet circles the star and turns on its axis, carving out the ordinary alternation of day and night and the familiar sweep of the seasons. The distribution of light with latitude and season sets broad belts of energy input. Near the equator, the near-constant angle produces a persistent surplus compared with higher latitudes. Toward the poles, there is a deficit over the year, as low angles and long dark intervals reduce the annual intake. In the outer frame, the essential point is that the star and orbit define where there is more light and where there is less, and when in the year those maxima and minima occur. The details of how that energy is shared among air, water, rock and life belong to later layers, but the template is set here by position, tilt and distance. Viewed from far away Earth in this interval, appears as a lit hemisphere turning through space, with the bright limb drifting from tropic to tropic over the year. The line between day and night slides continuously, creating mornings and evenings that pass like a wave across the surface. The nearly circular path carries the planet around the star in a period that is familiar, while the star's output bathes the world in a steady glow, only slightly less intense than today. This outer scaffolding does not tell the full state of air and ocean, yet it fixes the cadence to which those systems must respond. Light arrives in a predictable pattern set by celestial mechanics that change slowly, and by a star that brightens over deep time. 600 million years ago, that pattern is already in place. Gentle differences in distance through the year, a tilt-driven exchange of hemispheric advantage and a spectral mix centered in visible light. The canvas of illumination is laid down first, and every process within the planet's envelope will take its place upon it in turn. Earth turns more quickly 600 million years ago, and that faster spin sets the tempo of every day, while the moon's pull raises and lowers the oceans with a stronger reach than in later ages. The day lasts about 21 to 22 hours, so sunrise and sunset come a little sooner, and the cycle of warming and cooling runs on a slightly brisker clock. Rotation is simply the spin of the planet about its axis. When the spin is faster, any point on the surface moves eastward a little more swiftly beneath the sky, and the boundary between daylight and darkness passes more often each year. The shorter day changes rhythms rather than totals. The year still holds the same broad supply of sunlight, yet the delivery is carved into more slightly shorter daylight portions and more slightly shorter nights, which shifts the timing of local maxima and minima in temperature and surface processes tied to them. The Moon stands closer to Earth in this interval and circles the planet more rapidly, so its gravitational tug on the oceans is stronger. A tide is the slow, steady rise and fall of the sea, caused by the varying gravitational pull of the Moon and the Sun as Earth spins and as the Moon moves along its orbit. Because gravity weakens with distance, the ocean on the side of Earth facing the Moon feels a slightly stronger pull than the far side, and the water adjusts by forming broad bulges that are carried around by the planet's rotation. As the bulges sweep beneath a coastline, the sea level at that coast rises and then falls. With the Moon closer, the height difference between high water and low water tends to be larger on average than in later ages, though the actual range still depends on local basin shape depth and the narrowings and widenings that can amplify or mute the passing wave. The basic timing follows a familiar pattern. Most places feel 2 high waters and 2 low waters during a single solar day, because the rotating Earth carries each point beneath both the near bulge and the far bulge. In some locations, the ocean and the shape of the coast favour a once daily pattern instead, or a mixed pattern in which one high water is higher than the other and one low water is lower than the other. The shorter length of day changes the spacing between these events by a small amount, and the closer Moon shortens the length of the lunar month, so the sequence of stronger and weaker tides that depends on the alignment of Sun and Moon also runs on a shorter beat. The interplay of spin and tide is gentle but persistent. As the sea flows across the seabed and past headlands, friction resists the motion and dissipates a little energy as heat. That friction is the physical reason the tides very slowly slow the rotation of Earth and push the Moon a little farther away over very long spans. In the period considered here, that slow exchange is still partway through its long course, so Earth turns faster and the Moon orbits at a smaller distance. The spin rate also shapes how moving water curves. On a rotating sphere, any motion that tries to go straight is deflected sideways, a tendency called the Coriolis effect. The strength of this deflection grows with the rotation rate and with the sign of latitude, so it is larger away from the equator and vanishes at the equator itself. With a shorter day, the deflection is slightly stronger at a given latitude than it will be later. When wind or a passing pressure change sets the surface layer in motion, the path of that moving patch of water bends to the right in the northern half of the planet and to the left in the southern half. After the initial push fades, the water can trace wide slowly, turning loops called inertial motions, whose period depends on the spin rate and latitude. A faster spin shortens that period so the loops complete in a little less time. This curved tendency shapes the sweep of tidal currents as well. When the tidal wave enters a basin, it often rotates around points of very small tidal range, and the sense of that rotation depends on hemisphere. The faster background spin nudges these paths and slightly changes how far and how fast the tidal signal reaches along a coast. The shorter day also adjusts daily heating. Morning light begins to warm the ground, and the thin skin of the ocean local noon arrives a little earlier, and evening cooling begins a little earlier. Because the daylight window is slightly shorter, there is a little less time for surfaces to take in energy before night returns, and then a little less time for cooling before dawn, so the timing of the day's highest and lower surface temperatures shifts. Over the oceans, the twice daily rise and fall of the sea level, combined with the back and forth tidal current, stirs the thin surface layer each few hours. Even where the wind is calm, that steady stirring mixes warmer water from the top, few handspans downward, and draws slightly cooler water upward, smoothing sharp contrasts that might otherwise build through a long, still afternoon. Where the shore is broad and shallow, the tidal current floods across flats and retreats, repeatedly wetting and draining the surface. On each pass, the water shears over sand and mud and peels off small temperature differences set by the morning sun, so daily heating near the coast is moderated by the predictable sweep of the tide. The closer moon and the faster spin strengthen this effect by modest degrees. Twice daily flushing reaches farther inland along channels, slack water intervals become slightly shorter, and the tide's pumping of near-shore layers is a little more effective. The shape of Earth itself reflects the rotation. A turning planet is slightly flattened at the poles and bulged at the equator, because the outward tendency of rotation is greatest, where the surface speed is greatest. With a faster spin, the equatorial bulge stands out a little more. Sea level, which follows a surface of equal potential, sits a little higher near the equator relative to the poles than it would on a more slowly turning planet. The difference is not dramatic yet. It is present as a quiet background upon which tides ride. Superimposed on that background are long beats tied to the shorter lunar month. When the sun and moon line up, their pulls add and the high waters climb higher. When they stand at right angles, their pulls partly cancel and the range shrinks. With a closer moon, the difference between these phases is larger, and because the month is shorter, the transition between stronger and weaker tides comes a little more often. In broad bays and along open shelves, if the natural period for water to slosh back and forth happens to approach the period of the tide that drives it, the system can ring strongly a behaviour called resonance. Small shifts in the driving periods, whether from the shorter day or the shorter month, move a basin nearer to or farther from that special timing and subtly change how strongly it responds. The net picture is a world whose clock ticks a little faster and whose lunar tug is a little firmer. Days are a little shorter. The curve of moving water is a little tighter, and the rise and fall of the sea is a little more marked. The immediate consequences appear as timing, pacing, and gentle changes in the strength of regular motions. The stronger tidal reach gives coastal waters frequent stirring and repeated alternation between movement and slackness. The faster rotation sets how quickly a parcel of water turns when left to its own motion, and how paths bend when currents are set in motion. All of this unfolds as steady, predictable rhythm, not as sudden upheaval. Each place along a coast feels high water and low water in its own sequence set by geometry. Yet everywhere the combined effect of faster spin and closer moon is the same kind of steady nudge. The planet's rotation provides the metronome, and the tides provide the beat that moves the surface layers back and forth in time with that metronome. In this age, the metronome ticks a little faster, and the beat is a little stronger, and the hours pass with that quiet regularity. A planetary magnetic field surrounds Earth 600 million years ago, and stands between the solar wind and the uppermost air-gathering charged particles into a structured space environment that bends, guides, and sometimes blocks their paths. The field rises from motion within the liquid outer core, where convecting iron alloy moves through existing magnetic lines and sustains a self-exciting dynamo. Heat flows outward as the deep interior cools and light elements try to rise, while rotation organizes the fluid into columns that tend to align with the spin axis. Together, these motions generate a global dipole field that resembles a bar magnet offset by slow, irregular changes. Paleomagnetic records show that polarity reversals occur across geologic time, and that field strength wanders, and some studies propose intervals in this era when the dipole becomes unusually weak, though measurements remain sparse and their interpretation carries uncertainty. Whether strong or diminished, the field threads space and shapes a large cavity in the solar wind called the magnetosphere. Upstream of Earth, the supersonic wind meets resistance and forms a bow shock where particles heat and slow. Beyond this shock lies the magnetosheath, a turbulent layer where the diverted flow streams around the obstacle. The boundary of the obstacle is the magnetopause, a moving surface on which pressure from the solar wind balances the magnetic pressure and internal plasma of the planetary environment. Where the interplanetary field connects in favourable orientation with Earth's field, magnetic reconnection opens lines and lets solar wind plasma enter. Where the orientations oppose, entry. The boundary remains more closed, but it is never perfectly sealed. Downstream, the stretched field forms a long magnetotail, with a northern and a southern lobe separated by a thin current sheet. In that tail, energy from the stressed solar wind piles up and can be released in sudden bursts as reconnection snaps lines and flings plasma earthward and tailward. The released energy flows along magnetic lines toward high latitudes in each hemisphere and powers auroral emissions in the thin air near the top of the atmosphere. With a weaker dipole, the dayside boundary would stand closer to Earth on average, and reconnection could open larger regions to entry, so more particles reach the upper air, while with a stronger dipole the boundary would stand farther out, and the shield would be more resistant, though never absolute. Within the magnetosphere, trapped particles circle lines of force and bounce between mirror points, drifting slowly around the planet to form donut-shaped radiation belts. The inner belt holds mainly energetic protons born when cosmic rays strike the upper atmosphere and produce cascades that feed trapped populations. The outer belt hosts electrons and ions injected from the tail during disturbed times. Field strength sets how tightly charged particles spiral and how broad the belts can be. If the global dipole slackens, confinement shifts, and the zones of stable trapping narrow or retreat, helping more particles leak into the upper air or outward into space, while stronger fields keep more particles bottled. These populations wax and wane with solar activity. When a coronal mass ejection arrives, dynamic pressure jumps and the dayside boundary compresses. If the interplanetary field points southward relative to the planetary dipole, reconnection strengthens and energy floods the system. Substorms brighten auroras and drive convection in the magnetosphere, pulling cold plasma from the high-latitude ionosphere, heating it, and returning part of it sunward through the tail. The upper atmosphere responds in several ways. Particle precipitation deposits energy at altitudes where the air is thin and produces ionization and excitation that subtly alter chemistry. In an oxygen-bearing atmosphere, the production and destruction of reactive species respond to this input, and the heat load can make the upper air expand, raising the altitude where it becomes collisionless. A weaker magnetic shield would allow greater average precipitation for a given solar driver, potentially increasing the long-term rate at which the topmost air drifts away along open field lines, whereas a stronger shield would reduce that access. The escape pathways include thermal escape, where the hottest particles exceed the speed needed to leave non-thermal escape, where ions are picked up by fields and accelerated along open lines, and sputtering, where energetic particles knock neutrals free. Field topology regulates these routes by controlling how much area is threaded by open lines that connect to the solar wind. The polar caps, where lines open outward, act as valves. If the dipole weakens and the polar cap widens, the area of potential outflow grows, and the upward flux of light ions can rise while a stronger dipole narrows the cap. At the same time, the magnetosphere buffers sudden pressure pulses, so even a weak field moderates the most abrupt impacts. Electrical currents link the space environment to the upper air. The magnetopause carries a flowing current where the shocked solar wind slides past the boundary. The tail current sheets carry energy storage and release, and field-aligned currents stream along lines into the high-latitude ionosphere, closing through broad sheets in the upper atmosphere. These ionospheric currents flow through a medium whose conductivity is set by sunlight, particle precipitation, and neutral winds. As they vary, they apply drag to the neutral gas and transfer momentum that can drive winds at high altitude. Changes in the field strength and geometry alter where these currents close and how strong they can be. Over the oceans, the varying field also induces tiny electrical currents in conductive seawater, and those currents generate secondary magnetic fields that feed back on the main pattern by minute amounts, a coupled system that remains gentle yet continuous. The global dipole does not stand alone. Crustal rocks hold remnant magnetization that perturbs the field locally, and currents in the ionosphere and magnetosphere reshape the pattern on timescales from minutes to days. In this age, the balance among these sources still resolves into a dominant dipole, tilted slightly from the spin axis and drifting slowly across the globe as the dynamo evolves. Polarity reversals which swap north and south continue to occur, but each reversal occupies a brief geologic moment compared with the long stable intervals between. During a reversal or an excursion, the field may weaken, and the magnetosphere may shrink, expanding the reach of energetic particle access and shifting auroral zones equatorward. When the dipole recovers, the boundary moves outward and the auroras retreat poleward. Evidence for ultra-weak states in parts of this era suggests that the shield can become less effective at times, yet even a reduced field organizes space around the planet and constrains particle motion more than an unmagnetized body would. Across the sunlit and dark halves of the magnetosphere, the circulation of plasma follows a slow pattern. Fresh solar wind plasma enters on the day side through reconnection, convex over the poles into the tail stores energy in stretched lines, and returns part of that energy through earthward bursts that feed the ring current and expand the polar lights. On quiet days, this convection drifts languidly. On active days, it quickens. The magnetosphere breathes in response to the changing wind-moving boundaries outward with lulls and inward with gusts. Against this steady breathing, the long background level of field strength sets how large the system is and how easily particles penetrate. The presence of a magnetosphere also influences how cosmic rays reach the top of the atmosphere. A stronger dipole raises the rigidity cutoff and excludes more low-energy cosmic rays, while a weaker dipole lowers the cutoff and allows more to enter slightly, raising the production rate of cosmogenic nuclides and adjusting ionization at high altitudes. These changes propagate subtly into atmospheric electricity and cloud microphysics through complex chains that remain the subject of ongoing study and carry uncertainty in magnitude and persistence. Yet the first-order picture is firm. A geodynamo builds a global field. That field sculpts a cavity in the solar wind, and the cavity's size, shape, and permeability regulate energy and particle entry into the upper air. In the world 600 million years ago, this shield is present and alive with currents, lines, and drifting particles. Its strength can waver, perhaps to notably low levels at times, and during such intervals more energy and particles access the thin air near the top of the atmosphere, altering the structure and chemistry there, and raising escape along open paths. When the field stands taller, access subsides and the upper air grows quieter. Through all states, the magnetosphere remains a dynamic mediator between star and planet, translating the steady flow from the sun into structured motion light at the poles and gentle drag on the highest winds, a controller at the outer edge of the planetary envelope that sets conditions for the layers beneath. Air above Earth, 600 million years ago, is a layered envelope whose gases filter. Sunlight regulate heat loss and host reactions that alter themselves with height. Nitrogen provides most of the mass and sets pressure that declines steadily upward, a stable background in which more reactive species work. Oxygen holds a significant share that has risen since earlier oxygenation pulses, but likely stands below the modern fraction on average. Values vary across time and place in this period, so a range remains plausible. Carbon dioxide, methane, nitrous oxide and water vapour together form a thin thermal blanket called greenhouse gases. Each absorbs outgoing heat at specific wavelengths and then re-emits it, slowing the loss of energy to space. Compared with the intense icehouse episodes that precede this interval, carbon dioxide sits lower than peak glacial highs, and methane is constrained by the expanded presence of oxygen that removes it rapidly through oxidation. Water vapour remains the most abundant greenhouse gas near the surface, controlled by temperature, rather than direct sources, and declines sharply with height, as a cold trap near the tropopause condenses it out. From the ground to the base of the stratosphere, the troposphere holds most of the weather. In this lowest layer, temperature usually falls with height because the air is heated mainly from below by a warm surface and by the absorption of sunlight and re-emission of heat within the lowest kilometres. The rate of this decrease depends on moisture. Where the air is dry, the decline is steeper. Where it is moist, the release of latent heat during condensation softens the profile. The top of this mixed layer, the tropopause, marks a transition to a zone where temperature stops falling and can rise with height. That rise defines the stratosphere. It occurs because oxygen present in the air allows ozone to form when ultraviolet light splits oxygen molecules and free atoms recombine into three-atom molecules that absorb incoming ultraviolet radiation and convert it to heat. The exact abundance of ozone in this era depends on the available oxygen and on the balance between production and loss through reactions with hydrogen and nitrogen oxides, but even a thinner shield alters the vertical temperature pattern and screens biologically damaging wavelengths. Above the stratosphere, the mesosphere sees temperature fall again with height, as radiative cooling outpaces absorption, and above that the thermosphere warms under direct absorption of high-energy radiation by sparse molecules and atoms. The boundary that divides well-mixed lower air from compositionally separated upper air is the homopause. Below it, turbulent mixing smooths composition except for water and reactive species with short lifetimes. Above it, molecular diffusion sorts gases by mass. In that higher region, light species such as hydrogen and helium grow relatively more abundant with height. Where hydrogen reaches high enough energy, it can escape to space, a loss fed by the slow breakup of water, by sunlight, and by reactions that produce hydrogen-bearing radicals. The cold trap at the tropopause strongly limits how much water reaches these heights, so the rate of loss is governed by the supply of hydrogen that can cross that barrier. A higher oxygen background strengthens ozone formation and reduces methane lifetime, and both effects influence the cold trap by modifying lower stratospheric temperatures. Aerosols of several kinds populate the air and modulate radiation. Tiny sulfate droplets form when sulfur dioxide from volcanoes oxidizes, dust rises from dry land and shorelines, sea salt sprays upward from breaking waves, and organic particles can grow from gases produced by microbes and plants in later ages, though in this interval marine microbes already contribute precursors. These fine particles scatter sunlight and provide surfaces for reactions that make and break ozone and other compounds. Their lifetimes depend on size and height. Lower tropospheric particles wash out quickly with rain, while stratospheric sulfate from large eruptions can linger for months to years and alter the balance between incoming and outgoing energy by reflecting sunlight and absorbing infrared radiation. The greenhouse effect at this time rests on the combined spectral action of carbon dioxide, water vapor, and minor gases. Carbon dioxide absorbs in strong bands that are not easily saturated when pressure and temperature vary with height, and pressure broadening spreads its influence across a range of wavelengths. Water vapor absorbs in many bands and fills spectral gaps near the surface, yet its low stratospheric abundance leaves windows aloft that carbon dioxide and ozone partially cover. Methane, though lower in concentration under more oxidizing air, still contributes in regions of the spectrum where water and carbon dioxide are weaker, and nitrous oxide adds modest absorption where its bands overlap. The result is a layered radiative structure in which heat from the surface and lower air is absorbed and re-emitted many times before escaping, while incoming sunlight mostly passes through to warm the ground and the upper layers selectively. The presence of more oxygen than in deep earlier time allows a more robust ozone layer than before, though still potentially thinner than in the modern era. That layer shapes the vertical temperature profile and screens ultraviolet light in the range that splits DNA and other organic molecules. Its thickness can fluctuate with solar input particle precipitation from space volcanic injections of halogen-bearing gases and the balance of nitrogen oxides and hydrogen oxides that catalyze loss cycles. In this period, those cycles operate within an atmosphere that is still maturing chemically, with sources and sinks that differ from later ages yet follow the same underlying physical rules. Chemistry couples to dynamics. As air warms or cools, density changes and motions begin that move moisture and trace gases. Rising motion carries water vapor upward from warm surfaces until condensation forms clouds that reflect sunlight and block infrared radiation in complex ways that depend on height and droplet or crystal properties. The drier upper troposphere and lower stratosphere radiate efficiently to space-tying global heat loss to conditions near and above the tropopause. Winds then redistribute heat latitudinally. Near the equator, where sunlight is more direct over the year, warm moist air rises and flows aloft toward higher latitudes, descends in subtropical belts, and returns near the surface, a pattern that segments the lower atmosphere into overturning cells. These broad motions set where humidity is high and where it is low, which in turn controls the greenhouse role of water vapor and the formation of high clouds that influence how much heat escapes. Trace gases evolve through feedbacks that unfold over years to millennia. Greater oxygen reduces methane lifetime and pushes the atmosphere toward more oxidized states. Lower methane lessens greenhouse strength in bands where it is most active. Reduced greenhouse support cools the upper troposphere and can reinforce the cold trap, which further limits stratospheric water and reduces hydrogen loss. At the same time, volcanic inputs of carbon dioxide build or sustain baseline greenhouse capacity and silicate weathering on land, and seafloor removes carbon dioxide over long spans, a process that depends on temperature, rainfall, and fresh rock supply. In the air above, the sum of these interactions sets the vertical temperature profile, the strength of the infrared blanket, and the intensity of ultraviolet screening. Observational constraints for this era come from indirect signals preserved in rocks and minerals, rather than from direct measurements, so ranges and uncertainties remain part of the picture. Even with those limits, the broad features are clear. Nitrogen dominates and sets pressure. Oxygen reaches levels high enough to sustain widespread ozone and to shorten methane lifetime. Carbon dioxide sits at values that, together with water vapor, maintain a functional greenhouse without the extreme load associated with peak glaciations. Aerosols arise from volcanoes and from surface processes and modulate radiation for intervals that depend on their altitude and size. With altitude, the air shifts from a mixed moist lower layer to a compositionally stratified upper region where light gases become more common and escape pathways open slowly. Through these layers, light is filtered, heat is exchanged, and molecules are made and unmade in steady cycles. In this age, the air's composition and structure set a firm radiative and chemical framework upon which lower processes operate a stable but responsive cover that balances incoming sunlight against outgoing heat, while ultraviolet light is softened by ozone high above and water is trapped low enough to limit loss to space. Climate 600 million years ago stands in a post-glacial balance that follows the end of the great cryogenian ice ages, with ice-retreating oceans widening across low-relief plains and the combined action of sunlight, greenhouse gases, clouds and reflective surfaces settling into a state that is cooler than a hothouse, yet warmer than the deep freeze that came before. When ice pulls back, the planet's reflectivity drops. Reflectivity, called albedo, is the fraction of incoming light that a surface sends back to space, and bright snow and ice return much more light than dark ocean or wet ground. As white surfaces shrink, more sunlight is absorbed at the top few handspans of the sea, and the upper soil where land is exposed, and the extra absorption nudges temperatures upward, especially in seasons and latitudes where the sun climbs high. The resulting warming allows more water to evaporate, and water vapor in the lower air rises until cooling aloft forms clouds. Clouds can both reflect sunlight and trap heat, and their net effect depends on height, thickness, and droplet or crystal properties. In the tropics, where the sun stands high for much of the year, deep convective clouds rise from warm seas and build tall towers that reflect large portions of sunlight, while their cold tops radiate well to space, moderating local heating. In subtropical belts, clearer skies let more sunlight reach the surface, supporting warm, dry regions over ocean and land that feed dry air into the lower branches of the overturning circulation. Mid-latitude cyclones travel along temperature contrasts between warmer and cooler air masses and bring variable cloud fields and rain, while toward the poles, the lower sun angle and long dark seasons keep average temperatures low enough for sea ice to form in winter and retreat in summer, maintaining a band of seasonal ice that expands and contracts with the year. Greenhouse gases bridge the gap between sunlight in and heat out. Carbon dioxide provides a baseline absorber whose strength responds over long spans to the balance between volcanic supply and removal by chemical weathering. Chemical weathering is the set of reactions in which rainwater, carrying dissolved carbonic acid, slowly breaks down silicate rocks and ultimately sequesters carbon in carbonates and clays. The rate of this process grows with warmth rainfall and the exposure of fresh rock. After the ice retreats, freshly ground debris and newly exposed terrains offer abundant reactive surfaces, so as temperatures and precipitation rise, weathering accelerates and pulls down carbon dioxide, which cools the planet and restrains further warming and negative feedback that stabilizes climate. Methane, more reactive in an oxygen-rich air, holds lower background levels than in earlier ages, which limits its role in warming compared with carbon dioxide and water vapor. Water vapor set by temperature amplifies whatever baseline the other gases supply by adding broad spectral absorption whenever the air is warm and moist. Together, these components sustain a climate that keeps liquid water widespread in oceans and shallow seas and leaves permanent ice mainly at high latitudes or high elevations, with seasonal coverage extending farther during cold parts of the year. The oceans mediate much of the climate's inertia. Mixed layers in the upper tens of meters store heat gained in sunny months and release it later, smoothing swings between seasons and carrying warmth poleward through slow currents that slide along the edges of basins and through interior pathways steered by planetary rotation. Wind-driven gyres circulate in opposite senses in the two hemispheres and create regions where surface waters pile up and others where they're drawn away, lifting cooler water from below in places where winds and geometry favour upwelling and pushing warm water downward where convergence occurs. The net effect is to redistribute heat in patterns that align with the prevailing winds and with the shape of the coasts and shelves of the time. Seasonal cycles imprint themselves on this moving surface. In summer at mid and high latitudes, the mixed layer warms and shoals as sunlight penetrates, and wind stirring competes with stabilizing density stratification caused by warming and freshening from ice melt or rain. In winter, stronger winds and surface cooling deepen the mixed layer and allow the release of stored heat, sometimes reaching down to bring nutrient-rich waters upward, which matters for plankton in later narrative layers, but here mainly alters the balance of heat. Sea ice forms where the surface cools below the freezing point, adjusted for salinity, rejecting brine, and densifying nearby waters, a process that can help set cold, heavy surface waters in motion along the seafloor. The extent and duration of sea ice affect albedo and insulation. A skin of ice blocks direct ocean heat loss to the air and traps heat beneath, while open leads and polynyas vent stored warmth and moisture back into the atmosphere, fueling cloud and snow production. Over land, the climate inherits gentle topography left by long erosion and by the levelling influence of past ice. Low relief allows shallow seas to spill far inland when sea level rises, spreading the marine influence into continental interiors and damping temperature contrast between land and ocean along margins. Where land remains high, orographic lifting forces air upward, cools it, and wrings out moisture as rain or snow on windward slopes, while leeward regions lie in drier shadows. Vegetation on land is limited in this period, so the land surface presents broad expanses of rock soil and microbial films whose colour and roughness influence how much energy is absorbed and how quickly heat is exchanged with the air. Dust can lift from arid regions, and the edges of retreating ice ride winds for days and settle into the ocean and onto glaciers. Dust on snow darkens the surface and hastens melting, while dust in the air scatters sunlight and cools the ground beneath by a small amount. Both effects depend on timing and concentration, and both play out as gentle modifiers rather than primary drivers. Variability within this climate arises from the slow dance of orbital cycles that adjust seasonality over tens to hundreds of thousands of years, from changes in volcanic outgassing that alter carbon dioxide on still longer spans, and from the internal dynamics of ocean and atmosphere that shift storm tracks and rainfall belts year by year. On human scales, such variations would feel like changes in wet and dry years, harsher or softer winters, and longer or shorter warm seasons at a given place. On geological scales, they write patterns into sediments as alternations in grain-size mineral content and isotopic ratios that echo the pacing of the external and internal controls. Following the end of global-scale glaciation, distinct layers of carbonate deposited directly atop glacial sediments, often called cap carbonates, indicate rapid chemical and physical responses at the ocean surface to the drawdown of carbon dioxide and to the sudden change in weathering and runoff. By the time of this interval, those transient signals have passed, but the legacy remains in a world where sea level is high, shelves are wide, and the climate system has recovered a steady state that supports expansive shallow waters and mild temperatures across many latitudes. Rainfall patterns mirror the circulation. Rising motion near the equator feeds bands of frequent rain and towering clouds that migrate with the seasons. Subsiding dry air under subtropical highs favors deserts and clear skies. and alternating wet and dry spells accompany the passage of travelling lows in mid-latitudes. Thunderstorms ignite where warm, moist air surges upward over heated surfaces or along boundaries between air masses, releasing latent heat and lofting condensation into anvils that spread high and wide. Lightning and heavy downpours reshape surfaces by breaking soils, carving channels, and transporting sediment toward coasts. Over longer spans, the balance between precipitation and evaporation helps set the salinity of enclosed and semi-enclosed seas, which in turn affects density circulation and sea ice coverage in local ways that feed back onto regional climate. Yet the global mean remains a tempered state supported by a sun only modestly dimmer than today, and by a greenhouse blanket that is neither starved nor extreme. Uncertainties belong to the exact levels of gases to the distribution of a land near the poles that would set how readily large ice sheets can regrow, and to the behaviour of clouds whose net radiative effect depends on microphysics poorly recorded in rock. Even with these uncertainties, the broad pattern is firm. The planet leaves the extremes of the cryogenian behind and holds to a climate with liquid oceans stretching widely, with seasonally shifting belts of cloud and rain, with mid-latitude storms that pass in trains, and with polar caps that grow and shrink with the light. This state is resilient so long as weathering continues to draw down carbon dioxide in step with volcanic supply, and as long as the distribution of land and ocean favours efficient heat movement from equator to pole. In this balance, the world breathes in long, slow rhythm, a settled background upon which surface waters winds and seasonal ice trace their repeating patterns year after year. Continents 600 million years ago stand in a shifting arrangement that reflects the closing act of one supercontinental cycle and the first movements of the next, with large plates suturing along long mountain belts, while new rifts begin to open shallow seaways between departing blocks. The geometry at this time shows a great cluster of land centered in southern latitudes, often referred to as a short-lived supercontinent configuration that concentrates many cratons into a broad asymmetrical mass. Within this cluster, the great southern aggregate that becomes Gondwana grows as Africa, South America, Antarctica, Australia, Madagascar, Arabia, and the Indian Shield link together along fresh sutures. These sutures record the welding of once distant fragments through the collision of arcs and microcontinents that ride the last flows of oceanic plates into subduction zones. The scars left by these collisions run for thousands of kilometres and include belts known from later mapping as the Arabian-Nubian Shield, the East African Origin, the Mozambique Belt, the Kunga Belt, and the Damara and Zambezi systems, where ancient ocean floors have been driven under and crust has thickened, metamorphosed, and risen. The crustal roots beneath these belts grow dense and rigid, and their highlands feed long trains of sediment toward adjacent basins. To the north of this southern mass, other large blocks stand apart or in the process of departure. Laurentia, the ancestral core of North America and parts of Greenland, lies mostly in low latitudes and is edged by a mix of old mountains and new passive margins where rifting has stretched the crust and allowed thin early oceans to flood in. Baltica, the nucleus of northern Europe, occupies temperate to subtropical latitudes and trends along a separate path that will carry it across great distances in later ages, but at this time remains a distinct raft with both active and quiet coasts. Siberia stands farther away, a compact craton with its own ring of older mountain belts and emergent shelves. Between these blocks, oceanic plates dive at trenches or spread along ridges, building a patchwork of basins that differ in age depth and heat flow. Where rifts have just opened, the lithosphere beneath is warm and buoyant, so seafloor stands higher and basins are shallow. where crust has spread for many tens of millions of years, the cooling plate contracts and deepens, creating broader abyssal plains. Along the growing edges of Gondwana, subduction zones chew landward beneath continental arcs. Magmas rise to build long chains of volcanoes that dot the margins of what will be South America and Antarctica, and that line the length of what will be Australia and parts of Africa. Behind these arcs, the crust stretches and basins open that trap thick piles of volcanic ash lavas and eroded products of the rising ranges. Farther inward, the collision belts that united the cratons still warm the lower crust and support broad plateaus with gentle gradients where rivers thread between ridges and carry sand silt and dissolved ions toward encircling depressions. The distribution of land across latitude places much continental area near the equator and in subtropical bands where sunlight is strong and winds are steady. At these latitudes, low relief surfaces abut wide continental shelves along which tides and waves will operate when seas sit high, and along which later shells, grains and mats will accumulate. But here the tectonic fact is foremost: the shelves exist because buoyant continent meets denser oceanic plate along rifted and once rifted margins, and the crust steps down in a quiet transition from thick blocks to thin edges. In the high southern latitudes, parts of this cluster extend toward colder zones, and the position of the collective centre of mass near the pole allows mountain glaciers to persist on elevated ground, even as global climate recovers from earlier extremes. Paleomagnetic directions frozen into rocks indicate that many of these cratons lie with their ancient norths pointed in differing directions, and their inclinations suggest a concentration of land in southern latitudes that is consistent with the suturing underway. Rates of relative motion are modest in human terms and swift in geological ones, of the order of a few centimetres in a year, so in the span considered the coasts shift by distances that stack up only over millions of years, while the internal belts continue to uplift and erode. Along the edges where spreading begins, narrow oceans form. One such system opens between Laurentia and parts of the southern mass, and early stages of ocean formation produce a chain of embayment straits and fault-bounded depressions. These features are controlled by the orientation of old sutures and the weak zones they leave behind, which guide where new fractures exploit the crust. As rifting advances, the continental crust thins by the stretching and unzipping of long blocks along normal faults. Volcanic intrusions fill space as the mantle decompresses and melts, and the base of the crust warms. Hot young lithosphere stands high and is slowly replaced by denser cooler lithosphere as time passes. Where rifting fails, aborted arms remain as long linear basins on land that subside gradually and fill with sediment shed from nearby highs. The interior of the southern cluster holds large depressions with slow subsidence rates, where the crust bends under the weight of mountain belts and their loads of sediment. Flexure creates foreland basins adjacent to the origins, and these basins act as sinks that catch coarse material close to the rising ranges and finer material farther out, building structured wedges that thicken toward the mountains. Beneath the basins, heat flow declines with depth and distance from magmatic centres, and compaction tightens pores in growing piles, gradually welding grains and cementing them. The story of continental arrangement also includes the shallow roots of ancient cratons, which are thick keels of cold, buoyant lithosphere that resist deformation. These keels under Africa, under parts of Antarctica, under the Indian Shield and under Western Australia help stabilise the nascent Gondwana by pinning down corners and edges while belts between them absorb strain. The keels deflect asthenospheric flow and steer mantle upwellings into gaps between them. Where small upwellings touch the base of the plate, localised heating and thinning can help initiate rifts, and where cold keels project seaward margins can become irregular and embayed. The coasts that result are not smooth arcs but broken outlines with promontories, gulfs, and tapered corridors that reflect the inheritance of deep structure. Ocean gateways between separating plates control how water can later move from basin to basin. Yet at this level, the tectonic fact is simply that passages exist or close, depending on the spacing of opposing coasts and the elevation of intervening sills set by ridge crests or microcontinental blocks. The continental crust itself is a mosaic of terrain stitched together through older cycles, and their varied ages and compositions matter for how they weather and how fast they erode. Felsic highlands break down into quartz-rich sands and fine clays. Mafic belts supply denser minerals and more soluble ions. Where new arcs grow fresh volcanic glass and crystals weather rapidly, sending a pulse of reactive material toward nearby depressions. In contrast, old stable interiors yield coarser, more durable grains and provide long, smooth slopes. Across the cluster, the arrangement of arc belts, sutures, interiors and rifts sets a checkerboard of relief and subsidence. This patchwork defines where highlands shed debris and where basins can accept it. It also defines the length and gradient of rivers that link heights with edges. Long, low gradient rivers wind over gently tilted surfaces on craton tops. Short, steep rivers descend from young mountain flanks. Broad distributive networks spread across lowlands where the slope dwindles. The map is alive with motion, yet the positions of the largest pieces remain coherent in this interval. Gondwana enlarges and tightens along its belts. Laurentia maintains low-latitude positions with new margins along parts of its rim. Baltica and Siberia travel their own paths, and intervening oceans adjust their width as ridges create and trenches consume crust. At depth, the mantle circulates, lifting hot material beneath spreading centers and drawing cooler material downward beneath subduction zones. This conveyor couples to the plates at their undersides and supplies the energy that moves them. The balance between ridge push from high-standing, spreading centers, slab pull from sinking plates and basal tractions from the flowing mantle governs velocity vectors and explains why some coasts lengthen while others compress. Over time, the feedback between mountain building erosion and isostatic rebound keeps ranges from staying at extreme height for long spans, and the transfer of mass from uplands to basins stiffens the crust where loads gather and relaxes it where they are removed. In sum, the continental arrangement at 600 million years is a landscape of assembly and early dispersal. Large cratons have welded into a southern giant through broad belts of metamorphism and deformation that still rise as subdued but extensive uplands, while rifts on the margins and within some fragments signal the next cycle. The juxtaposition of thick, stable interiors, young mountain chains and nascent passive margins builds wide zones of low relief adjacent to deep basins and sets great stretches of coast at low latitudes. The plates continue to glide at their slow, steady pace atop the convecting mantle, and their boundaries mark where crust is consumed, where new crust is born, and where it is simply thinned and flexed. This geometry fixes the stage on which later surface processes will act, but in its own right, it is the changing map of the planet written in sutures, arcs, rifts and keels that hold the continents together, while the oceans adjust around them. Sea level stands high 600 million years ago and spreads quietly across low continental interiors, turning broad plains into shallow epicontinental seas whose beds lie within the reach of ordinary waves and tides. The height of the ocean surface relative to the continents reflects several controls that act together. Melted ice from earlier glaciations adds water to the basins. Warmer average waters occupy slightly more volume, a property called thermal expansion, which lifts the global surface by small but meaningful amounts. The shape of the basins also matters because young warm oceanic lithosphere stands higher than older cooler lithosphere. Where mid-ocean ridges are vigorous and wide, the average depth of the floors is shallower, and the same volume of water will sit higher against the continents. Finally, the continents themselves flex and shift. Where mountain belts load the crust, the lithosphere bends and local seas deepen. Where erosion removes mass from highlands, rebound lifts adjacent regions, and along margins that have recently rifted, thermal subsidence gently lowers long tracts of crust through time. The sum of these influences sets a relative sea level that in this interval floods far inland over surfaces of very low slope. These epicontinental seas differ from open oceans in depth, energy, and connection. A shelf, only a few tens of meters deep, can extend hundreds of kilometers inland, where slopes are extremely gentle, so a change of only a few meters in relative level can shift a shoreline by many tens or hundreds of kilometers. Because the floors are shallow, incoming swells feel the bottom far offshore, transform and break in broad belts that migrate with the coast. Tides traverse these interiors along paths controlled by the outlines of gulfs and straits, and by the depths of passages that link them to the open sea. Where resonant lengths and tidal periods align, ranges grow larger and currents quicken. Where they do not, tides remain modest and slack water intervals last longer, in all cases predictable twice daily, and once daily rises and falls, wet and drain flats scour channels and stir the thin layer of water that warms during the day and cools at night. Sediment supply shapes how these seas fill. Rivers deliver sand, silt and clay from uplands that still shed the products of earlier collisions. Where coasts face persistent wave approach, longshore drift winnows river deposits and builds strand plains and spits that march along the margin. Where coasts lie in the lee of headlands and embayments, deltas advance lobe by lobe into quiet waters and then subside under their own weight, leaving stacked packages that thicken seaward. From the seaward side, storms push reworked shelf sands landward to build shoals that migrate toward the coast, and sometimes weld to it, creating new barriers and lagoons. The interplay between accommodation and supply governs the shoreline position. Accommodation space is the depth and breadth available for sediment to accumulate below sea level. When relative sea level rises faster than sediment arrives, water covers new ground and shorelines retreat. When supply keeps pace, coasts hold position. When supply outstrips rise, coasts advance seaward. Because slopes are so low, the same volume of added or removed sediment can shift the coast far across the plain, and sequences of shoreline positions step back and forth through time as slow changes in subsidence, water temperature and sediment yield alter the balance. Water properties within these flooded interiors vary with connection to the open ocean and with the climates of their catchments. Near wide inlets, salinity remains near ocean values, and clarity is high in months with limited river input. Farther inland sills at straits and banks that separate basins can restrict exchange, allowing seasonal stratification to persist, with warmer, lighter water above and cooler, denser water below. In arid belts, strong evaporation and small river supply drive salinity upward in summer, and the chemistry approaches thresholds where calcium carbonate mud can precipitate directly from seawater under agitation, especially over clean, well-lit shoals. In the most restricted arms, salts can form when water shrinks in dry seasons and later redissolve when wetter months return. In humid belts, broad river mouths freshen. Surface layers carry fine suspended mud far from shore, and set up estuarine circulation in which lighter surface water flows seaward while slightly denser bottom water creeps landward beneath it. On the sea floor, the energy of ordinary waves and currents organizes recognizable textures. In the shore face, where breakers are common, sand forms low ripples and hummocks, and passing storms drape sheets of coarser grains that thin landward and seaward. Farther from the surf fair, weather motion weakens and mud can settle between events, building thin layers of silt and clay, interrupted by sparse sand streaks when stronger flows return. In vigorous tidal inlets and channels, sand and shell fragments gather into dunes that migrate along the bottom and leave cross-sets in the accumulating record. Over especially broad, clean shoals where agitation is frequent and water is clear, small, nearly spherical carbonate grains can grow by repeated coating of tiny nuclei, and these accumulations build low banks that shift with currents and storm bursts. The geometry of the flooded interiors reflects the inherited fabric of the continents. Failed rifts subside as long linear gulfs with central deeps and marginal shoals. Flexural troughs along mountain belts provide foreland basins that accept thick piles of sediment and deepen toward the rising ranges. Stable craton tops support exceedingly broad, exceedingly shallow plains of water where the seabed lies within the depth reached by storm waves across almost the entire width, so the bottom is reworked frequently and accumulates as thin packages that cover great areas. Across these settings, the positions of inlets and the presence of low sills control how tides and dense winter waters can enter and leave. Where passages are deep and wide, exchange is strong and interior seas ventilate readily. Where passages are shallow and narrow, exchange is weak, and interiors can hold seasonal density layers that persist until surface cooling or storms destroy them. Because slopes are very low, the coastline is sinuous and sensitive. Tidal channels branch and rejoin across flats. Inlets open during rare, extreme storms and then close over calmer years as sand drifts along shore. Barrier islands migrate landward over their own washover sheets, under the combined push of rising water and storm overwash. Marshes and tidal meadows occupy low back barrier lands, trapping fine sediment that lifts the surface toward equilibrium with the mean tide and dampens waves in narrow bays. Where waves dominate and sand is abundant, beaches stack shore-face sand in shallow seaward dipping beds and step landward in a staircase of former positions. Where mud supply is high, broad tidal flats build with subtle ridges and shallow runnels that guide ebb and flood. Seaward of the interiors, the open shelf acts as both source and conduit. When seas stand high against steep margins, shelves narrow, and the shelf break lies closer to land, bringing storm influence across a larger fraction of the platform. When margins are gentle, shelves widen and interior seas connect through broad passages. Exchange across these passages depends on sill depth and on the seasonal contrast between dense winter waters and lighter summer waters. In cold months, cooling, and where present sea ice formation can create heavier near-surface layers that sink and creep along the bottom into basins until friction and mixing slow them. In warm months, lighter waters spread from sunlit shallows, and from river plumes and winds drive them along coasts in currents whose direction follows the hemisphere's rotational tendency. Through the rise and the slow adjustments that follow the record of flooding, writes itself into the subsurface in recurring patterns. As coasts retreat, shore-face waves erode underlying deposits and leave a ravinement surface that smooths earlier textures. Over this surface, thin, widespread layers accumulate where sediment delivery is low and water is deep enough to mute frequent reworking. When relative rise slows and supply begins to fill available space thicker, nearshore bodies prograde and build seaward again. These names and patterns summarize the gentle alternation between creation of space by water and the filling of that space by grains carried from land or grown in place on the seabed. The physical image of rising seas in this time is one of steady measured change. Shorelines shift across their own deposits at a pace that averages only millimeters in a year when measured over long spans, yet the cumulative effect is a coastline displaced far inland and a continent face remade in calm water. Dunes that once stood at the limit of spray can after many centuries lie beneath clear shallows. Tidal flats that dried twice daily can, after a slight further rise, sit permanently below the level where wind can ruffle their surface. Every small step alters how waves break, how tides run, and how sediment moves, and those alterations feed back on the next step by changing how easily space can be filled. In this age of high water, the continents carry wide belts of shining inland seas, connected to the open ocean by straits and sounds, and the quiet advance of those waters sets the template for the layers that settle the channels that wander, and the beds that keep the story of the rise. Oceans 600 million years ago circulate under a pattern set by wind's tides, planetary rotation, basin shape, and the quiet engine of density contrasts between warm, fresh surface waters and cooler, saltier depths. Density depends on temperature and salinity. Warmer water is lighter, colder water is heavier, fresh water is lighter, salty water is heavier. Where sunlight and rainfall keep the upper ocean warm and sometimes fresh, a stable lid forms that resists mixing with the heavier waters below. This lid, often only tends to a few hundred meters thick, hosts the main seasonal changes and feels the daily tug of winds and tides, while below it a thermocline marks a rapid drop in temperature, and in many regions a halocline marks a rise in salinity. Together these gradients build stratification that slows the exchange between surface and deep layers. Over broad low-latitude belts, steady trade winds push the topmost waters westward. On a rotating planet, this push is not direct. Wind stress sets the surface layer moving at an angle and entrains water beneath it into a spiral of layers that turn and slow, with depth, a structure called Ekman flow. The net result is a transport of the upper ocean at right angles to the wind to the right in the northern half of the planet, and to the left in the southern half. Where winds diverge along the equator, or where they draw water away from a coast, the deficit is filled by the slow rise of cooler, older water from below a process called upwelling that brings deep properties to the surface and carries surface waters downward in flanking regions called downwelling zones. The wind-driven gyres that fill the subtropical oceans arise from this balance. Easterlies in the tropics and westerlies in mid-latitude set broad swirls that are narrowed and intensified on their western edges by the planet's faster spin at low latitudes and the changing Coriolis effect with latitude, a geometric constraint that packs flow into swift boundary currents. These currents move heat, salt, and dissolved gases laterally across entire basins, feeding warm waters poleward along western coasts and returning cooler waters equatorward elsewhere. Beneath the wind-stirred layer, the motion is slower and guided by basin contours and the gentle slopes of density surfaces. Long topographic waves too slow to notice from ashore carry adjustments along the edges of basins and communicate changes in wind stress and pressure around the rim. In the interior, broad sheets of water slide along surfaces of nearly constant density, creeping around seamounts and rising slightly where those surfaces bend upward, sinking where they bend downward. The deep branches of circulation are driven where surface waters become dense enough to sink. In cold high latitude, seas winter cooling and the growth of sea ice increase density at the surface. When sea ice forms, it rejects salt into the surrounding water, a process that raises salinity and can tip surface layers past a threshold, where they plunge, starting slow cascades that spill over sills and settle along the bottom as new bottom waters. In enclosed or marginal basins at lower latitudes, in contrast, strong evaporation can raise surface salinity until dense layers slide down slopes and feed intermediate depth currents, rather than the deepest limb. The exact sites and strengths of these sources change with basin geography, soil depths, and the pattern of wind and heat loss. The oceans in this period also carry chemical signatures that reveal a tendency toward poorer oxygen conditions at depth in many regions. The stable surface lid limits the supply of oxygen to deeper layers, and where deep exchange with the atmosphere is weak, oxygen taken up by the surface can be consumed below faster than it is replaced. When deep waters originate in settings with modest oxygen to begin with, or when the path to spread that water across a basin is narrow and slow, the interior grows oxygen poor. In some basins, iron-bearing waters persist at depth, a state called ferruginous that reflects both the chemistry of supply and the slow renewal of the deep layer. The degree of stratification is central. If seasonal cooling and storms can break the lid often and deeply, ventilation strengthens and oxygen penetrates farther. If the lid holds firm for long periods, interior waters age, chemical gradients sharpen, and the ocean's vertical contrast increases. Tides and internal waves provide one of the few persistent ways to leak energy downward and mix layers that are otherwise separated. As the barotropic tide, which is the surface tide familiar from coasts, runs over rough topography, it generates internal tides that slosh along density interfaces and break on slopes and seamounts. Where these internal waves run into steep terrain, they overturn and stir, dragging heavier and lighter layers into contact. In straits and over sills, this breaking can be strong enough to inject dense water upward and light water downward, eroding the sharpness of the thermocline and halocline locally, and feeding a slow background diapycnal mixing that is essential to close the global circulation. Storms deepen the surface mixed layer as winds strengthen and waves grow. The extra momentum reaches beneath the fair weather limit and entrains water from below, cooling the surface and warming the upper thermocline by small amounts that integrate over seasons. In some mid-latitude regions, winter mixing can reach hundreds of meters and leave behind a uniform layer that later restratifies in spring as sunlight returns and winds calm. The seasonal march thus builds an annual rhythm in which layers separate and merge predictably, stamping a cycle onto the slow background motions of the basins. Geometry fixes much of the path. Narrow equatorial waveguides allow swift planetary waves to run along the equator and reflect from eastern and western ends of basins, adjusting currents to match wind changes with little delay at low latitudes. At higher latitudes, changes propagate more slowly and shape the broader gyres. Where continents nearly close, a basin's shallow sills throttle the exchange between adjoining seas. A shallow sill blocks the densest bottom water from passing and can trap an interior with its own renewal timescale, while surface layers above the sill still exchange with the open ocean. The result is a stack of water masses, each with its own origin, temperature, salinity, and oxygen level arranged by density and constrained by topography. Traces move along these layers in a pattern that is slow but inexorable. The upper ocean takes in gases from the air and loses them again where temperature and wind favour release. Currents carry those dissolved gases laterally. When a patch is pulled downward in a downwelling region, its content is sequestered, until it returns many years later somewhere downstream. Where upwelling raises older water, that water brings its chemical history with it, including the imprint of any long isolation from the surface. In the world of this time, many interiors show evidence that the oldest deep waters linger and renew, slowly consistent with strong stratification and modest deep formation in only a few regions. The energy budget needed to mix a stratified ocean is supplied by winds, tides, and the slow cascade of internal waves. The share from tides likely matters more than in later configurations because the broad, shallow shelves and numerous straits of this high sea level world generate internal tides efficiently. Each tide that runs across a sill or a ridge launches packets that travel into the interior break on distant slopes and feed the small but continuous stirring that allows the deep ocean to slowly climb density steps and return toward the surface. Without this background mixing, the overturning would halt as dense water pooled in abyssal depressions. With it, though weak, a conveyor persists that balances sinking with gradual return. Salinity patterns reinforce the structure. In the subtropics, evaporation leaves surface waters saltier. In high rainfall, belts precipitation and river input freshen the surface. Where saltier water is cooled, it sinks more readily. Where fresher water is cooled, it resists sinking. These contrasts help set where intermediate and deep waters are formed. The close arrangement of continents in southern latitudes and the presence of wide shelves alter the sources compared with later ages, favouring marginal seas and shelf edges as formation sites and limiting the spread of the deepest limb through sills. Thus, the circulation that results is layered and regionally distinct rather than a single swift global overturning. Over the long spans of this interval, small drifts in wind patterns, the opening or closing of narrow passages, and the background climate all modulate the strength of stratification. When winters grow slightly harsher in a source region, sinking pulses more vigorous waters into the interior. When summers lengthen and surface warming intensifies, the lid thickens and the push weakens. Yet the basic picture stays the same. A wind-driven surface engine sets gyres and boundary currents that shuttle heat and salt. A density-driven interior engine forms heavy waters in a few favoured places and spreads them along the bottom and at intermediate levels. Tides and internal waves quietly spend energy to mix across density steps and keep the return path open. Oxygen is plentiful near the top and declines with depth, where renewal is slow, with many deep basins bearing the legacy of long isolation and limited ventilation. The oceans move with this slow grace, their surface a restless skin, and their interior a patient array of layers sliding past one another along sloping plains set by pressure, temperature, and salt. Seawater chemistry, 600 million years ago, rests on a set of linked cycles that transform carbon-oxygen, sulfur-nitrogen, phosphorus, silica-iron, and many trace metals as water flows from shelf to slope and into deep interiors. The carbon system frames the whole ocean. At the surface, carbon dioxide from the air dissolves and partitions among bicarbonate and carbonate ions, setting a mild alkalinity that keeps seawater slightly basic and allows calcium carbonate to precipitate where saturation is high and agitation is frequent. Alkalinity rises with the delivery of dissolved ions from continental weathering, which accelerates after ice retreats, and fresh rock is exposed along long mountain belts and newly cut river paths. In warm, clear shallows, the product of calcium and carbonate ion activity surpasses the threshold for precipitation, so carbonate muds and grains grow on the seabed, while in more turbid interiors the same ions remain in solution and travel onward. The ratio of magnesium to calcium in the water favours the growth of aragonite and high magnesium calcite, a consequence of ridge-controlled magnesium supply and the balance of hydrothermal uptake and river input. So the mineral form that cements shoals and laces microbial carpets reflects that ambient chemistry. Carbonate saturation varies with depth because pressure, temperature and dissolved carbon shift with the water's age and path. In deeper interiors that are cooler, richer in dissolved carbon, and poorer in oxygen, carbonate dissolves more readily, and the line that marks where dissolution begins shoals or deepens depending on how strongly the interior is ventilated and how much carbon accumulates there. The oxygen and sulfur cycles couple tightly to this vertical contrast. Surface mixed layers in contact with the air and stirred by wind and tide carry oxygen in abundance, but stratified basins and slow exchange leave much of the interior with low oxygen, and in many regions with iron-rich conditions that persist because oxygen is not present to hold iron in an oxidized insoluble form. In these ferruginous waters, dissolved iron remains mobile and can rise toward the redox cline, the boundary across which oxygen disappears and reduced species appear. Where a shelf or a restricted basin collects organic matter faster than oxygen can be supplied, environments develop in which sulfate reduction becomes the dominant pathway for breaking down organic remains. Sulfate delivered by weathering and by the oxidation of volcanic sulfur through the air and in the sea has increased from the very low levels of earlier deep time, yet still stands below the abundance of later eras, so the ocean holds enough sulfate to support widespread microbial reduction without reaching the modern richness of that ion. When microbes reduce sulfate, they produce sulfide that react with dissolved iron to form iron sulfide minerals first as metastable phases and ultimately as pyrite, and these tiny grains lock away both iron and sulfur and remove them from the water. Where sulfate reduction runs to completion in the presence of abundant organic matter and iron, dissolved sulfide can accumulate in the water itself, a state called euxenia that likely remains patchy and transitory on open shelves, but more persistent in restricted arms and deeper sills, leaving chemical fingerprints in sedimentary iron, sulfur and trace metal patterns. The distribution of ferruginous and euxinic states depends on ventilation productivity in overlying waters, the geometry of basins and the incoming flux of iron from hydrothermal springs and weathered land. Hydrothermal vents along ridges and in back-arc basins supply reduced iron and manganese, enrich the water in silica, and add metals such as copper, zinc and molybdenum in amounts set by temperature and rock composition. As those fluids mix with ambient seawater, they precipitate metal-rich particles that fall out nearby, while a fraction of dissolved load spreads along density surfaces and into interior basins where redox state then dictates whether those metals remain in solution, adsorb onto particles or are buried. Trace metal availability responds sharply to redox. In oxygenated water, molybdenum is present as a conservative oxyanion and remains soluble, but under euxinic conditions it is scavenged into sediments. Under ferruginous conditions it is less easily removed than in euxenia, but can still be limited. Iron is abundant where oxygen is low, yet precipitates as iron oxides at any interface with oxygen, and as iron sulfide where sulfide appears, so it cycles rapidly at redox clines and within pore waters below the seabed. Phosphorus required for life and recycled through organic matter tends to be retained in oxic muds by adsorption to iron oxides, and to be released from anoxic muds when these oxides dissolve, a feedback that can sustain low oxygen states by feeding more nutrients to surface waters in restricted basins. Nitrogen passes among dissolved dinitrogen gas, nitrate, nitrite, and ammonium. In oxygenated layers, ammonia is oxidized to nitrate by nitrifying microbes. In oxygen-poor layers, nitrate can be reduced to dinitrogen gas by dinitrifiers, or to ammonium by dissimilatory reduction routes that return nitrogen to forms unavailable to photosynthesis, and that can limit productivity if ventilation remains weak. The partitioning among these routes in this time follows oxygen distribution and gives the ocean a vertical chemical zonation tied closely to stratification strength and mixing energy. Silica is supplied from rivers and hydrothermal springs and is removed mainly by mineral precipitation and by incorporation into silica-rich crusts and cements, because large skeletal silica producers are not yet widespread. With fewer biogenic sinks dissolved, silica can reach higher levels than later, so chert and siliceous cements form in pores and fractures and along seafloor surfaces where temperature and concentration favour them. Boron and strontium accompany the major ions and leave isotopic signals in carbonates that reflect the balance of river water, hydrothermal flux and global weathering style, while chlorine and sodium maintain the broad stability of salinity against short-term swings. Across shelves and interior seas, agitation, sunlight and chemistry converge to precipitate carbonate mud directly from seawater, where saturation is high and water is warm and clear. Oids and composite grains grow by concentric coating of tiny nuclei that roll under waves and tides and micrete coats, microbial films to stiffen mats, and form hard grounds in high-energy belts. In quieter arms where evaporation outpaces inflow, and exchange concentration rises toward thresholds where gypsum and other evaporate minerals begin to nucleate in brines, first seasonally and then more persistently if the basin remains restricted. The presence or absence of such deposits in the record depends on sills that throttle exchange on freshwater supply from rivers and on the course of climate over decades to centuries. Chemically, the path toward evaporates begins whenever concentration increases and calcium and sulfate approach their product threshold in warm, shallow settings. Within the seabed, pore waters conduct their own chemistry as soon as grains begin to accumulate. Oxygen penetrates only a short distance into mud where organic matter is present. Below that thin oxic skin, bacterial sulfate reduction produces sulfide that diffuses upward to meet oxygen or nitrate, if they are present, or else reacts in place with iron to build pyrite. Deeper still, methanogenesis can occur where sulfate is depleted and a narrow zone forms in which methane moving upward meets sulfate moving downward and is consumed by anaerobic oxidation, a reaction that precipitates carbonate cement and leaves isotopic marks in the carbon of that cement. These stacked reaction zones move upward and downward as the rate of burial changes and as the supply of reactive iron and organic matter waxes and wanes. The net effect is to transform dissolved ions into solid phases that bind the stratigraphy and to return other ions to the water in altered ratios. Across the open ocean, the whole is kept in balance by slow mixing that carries surface chemistry into the interior and returns deep chemistry to the top, where internal waves and tides inject energy, density steps, thin redox clines migrate, and short pulses of oxygen intrude to consume reduced species. Where stratification strengthens, reduced species accumulate, and the water below the chemocline ages chemically increasing, dissolved inorganic carbon lowering pH slightly, and easing carbonate toward dissolution, while driving iron and manganese into mobile forms. Through time, carbon isotopes in carbonate and organic carbon swing across broad excursions that reflect the storage and release of carbon within this coupled ocean and sediment system, with one large negative swing in this era, pointing to a reorganization of the carbon cycle that plays out entirely within the chemistry of water and pore space. In some, the ocean at this time is a layered chemical engine. The surface remains oxygen-bearing and alkaline enough to favour carbonate growth on warm shelves. The interior ranges from well-oxygenated in regions of strong renewal to iron-rich and even sulfide-bearing in more isolated basins. Hydrothermal inputs keep iron, manganese and silica in motion. Weathering feeds alkalinity, calcium and sulfate, and burial removes carbon, sulfur, phosphorus and trace metals into minerals that form at and below the seabed. Every gradient is shaped by the balance between stratification and mixing. Where exchange across layers is brisk, oxidants reach downward and stabilize carbonate saturation at depth. Where exchange slows, reduced species rise, trace metals shift speciation, and the chemistry stratifies more sharply. The seawater that fills the basins thus tells a coherent story of a world with high shelves, modest deep renewal, rising sulfate ferruginous interiors punctuated by restricted sulfide-rich zones, and a carbon system that keeps the water mildly alkaline while linking the sky above to the rock below through constant quiet reactions. Seafloors 600 million years ago build a quiet archive from volcanic rock, reworked grains, chemical precipitates and soft microbial skins that trap and bind the finest particles into firm pavements, so that beds record not only what arrives, but also how strongly the water moves when it arrives. Along mid-ocean ridges, basalt erupts in long fissures, where plates pull apart and pressure in the underlying mantle falls enough for partial melting. Lava quenches in seawater to form smooth sheet flows and bulbous pillow stacks, their glassy rinds cracking into shards called hyaloclastite that tumble a short distance downslope before settling as angular debris against still warm rock. Between eruptive pulses, hydrothermal fluids rise through fractures, leach metals from the new crust and vent at the seabed as shimmering plumes. Where those fluids cool metal sulfides precipitate and build mounds and chimneys, the heaviest particles fall out nearby, lining the axial valley with dark metal-rich sands and muds, while finer suspended material drifts outward and settles as thin metalliferous layers on young crust a little farther from the axis. As crust moves away from the ridge and cools it, contracts and deepens its surface blanketed by a cloak of fine grains that thicken steadily with distance and time. This cloak begins as a mix of wind-blown dust, volcanic ash and clays, altered from continental rocks, and it grows by the slow rain of tiny particles flocculated from the water column during calm intervals between passing storms. Where the water above is more isolated and poor in oxygen, reduced iron remains mobile and can stain the deepest layers greenish or grey, while where renewal is stronger, browner oxides coat grains and bind them together. On slopes that descend from shelves and platforms, gravity flows move pulses of sand and silt into deeper water when storms or earthquakes shake the source. A single pulse begins when a dense mixture of grains and water accelerates downslope, scouring the bed beneath and carving a shallow path. As the flow outruns its supply, it wanes, lofts, and settles into a graded layer from coarser to finer upward. These turbidites stack in sequences that tell of repeated triggers, with thicker beds, nearer canyons, and thinner beds farther on the fan, and with subtle changes in grain size and internal lamination that speak to the speed, thickness, and concentration of each surge. Between such events, hemipelagic mud accumulates millimetre by millimetre, embedding tiny shards of distant ash and faint flecks of iron oxide that drift from far plumes. Where basin shape focuses deep boundary currents, the slow, persistent sweep of water along the contour of equal depth builds mounded bodies called drifts and scours, bare patches where speed peaks. These contorite deposits lack the sudden grading of a single collapse, and instead show rhythmic alternations of silt and mud with low-angle internal laminae that lean gently with the prevailing flow, a signature of patient bottom-hugging motion that persists for seasons, years, and longer. Across broad shelves, the seabed lies within reach of fair weather waves and farther shoreward, within reach of ordinary tides. Even where this section keeps to the seafloor frame rather than later shallows, the record on outer shelves still registers storm influence. When a large disturbance passes, wave orbital motion can reach tens of meters down, and its combined shear with storm currents molds low relief, hummocky sets of laminae that undulate with wavelengths of meters and heights of hand spans a storm bed called a tempestite. In the weeks and months after the blow, calmer waters lay down thin veneers of silt and clay that drape the hummocks until the next event arrives. Over long spans, these alternations form packages that thicken and thin according to the storminess of the climate and the position of the shoreline as sea level shifts slowly. Microbial mats spread across many of these floors wherever light, clarity and quiet allow, and even in dimmer settings where organic films settle on grains and knit them together. A mat ground is a thin cohesive layer built by microbes that exude sticky substances. It traps passing grains, resists minor shear, and records the faintest currents as wrinkle marks and shrinkage polygons when exposed and re-immersed at very low energy margins. Where mats persist subtidally, they stiffen the bed and favour the growth of macritic carbonate coatings that turn soft fabrics into firm grounds. Under stronger agitation, rolling grains pick up concentric carbonate skins to become ooids that gather into bars and sheets, while on quieter flats mats bind very fine mud into smooth pavements. In deeper basins, the mat influence is less visible to the eye, yet present in the way organic films promote early cement that locks particles sooner than they would consolidate by pressure alone. Volcanic ash falls intermittently across all of these settings. Fine glass shards and crystals rain out from distant plumes or settle from water columns after nearer eruptions, forming thin pale seams that later alter to clays. These datable layers act as time planes tying the age of beds in one basin to those in another. On ridge flanks coated with metalliferous mud ash mixes with iron-rich particles to create distinctive laminated couplets that can be traced for kilometers. Closer to arcs, coarse pumice can float rafted by waves into shore-face belts, and then waterlogged and sunk where it makes porous layers that later collapse as pores fill with cement. The chemistry of the water and of the pore fluids below the seabed governs how soon loose grains become stone. In carbonate-rich settings, early cements grow as isopachous rims around grains and as fibrous linings within tiny cavities, strengthening the sediment within seasons to years. In silicoclastic settings, compaction expels water and brings grains into closer contact, while iron oxides and clays fill pores, where sulfate reduction and methane production meet within the shallow subsurface carbonate cements, with light carbon isotopic signatures precipitate and build irregular nodules and hard layers that can interrupt the otherwise soft column. Farther down, as temperatures rise with burial organic matter, yields bitumen and then hydrocarbons and clays, reorganize events noted here only as deep diagenesis that changes fabric and squeezes water without inviting a jump to later regions. On the abyssal plain beyond the easy reach of most storms, deposition is steady and slow. Millimetre-scale layers of brown and red clays accumulate with the dust of continents and the quiet fallout of altered ash. Manganese and iron precipitate from seawater out of proportion to the tiny flux of particles forming hard pavements and nodules that grow outward by thin concentric laminae across spans that require patience even on geological scales. These crusts drape bedrock highs and the tops of buried lavas where currents keep the surface clean of soft mud and allow the rarest atoms that attach to reach the substrate. Where the deep interior holds reduced iron in solution, its encounter with oxygenated infiltrating water at the seabed creates thin oxide skins that glue grains and stiffen the uppermost centimeters. Slope failure remains a quiet sculptor everywhere the seabed is inclined. As grains accumulate to angles near the limit of stability, as fluids overpressure layers by rapid burial or by gas release, or as small shakes arrive from distant faults, blocks detach and move downslope as slides and debris flows. They carry intact slabs that ride on pulverized bases, and they come to rest as jumbled diamictons with clasts floating in finer matrix. Subsequent thin beds drape these coarse patches, restoring the evenness of the record until the next failure. In canyons that cut shelves and slopes, tidal pumping and episodic density flows keep tholwegs clear and funnel sand repeatedly into the deep, so that fans lobe outward and abandon courses as avulsions open new paths. Each lobe shows a radial thinning of beds, a fining of grains, and a loss of internal traction structures toward its edges. The cumulative picture is a living conveyor from ridge crest to abyss, from shelf edge to fan, from fair weather veneer to storm bed, all paced by the energy of water and the slow, constant fall of fine particles through the column. Time appears in the thickness of mud between event beds, in the degree of cement along grain contacts, in the number of ash seams crossing a stack, and in the alteration of glass to clay. Energy appears in the height of cross-sets, in the sharpness of scours at the base of turbidites, in the amplitude of hummocky laminae, and in the sorting of grains within a bed. Microbial mats, though soft, strengthen the archive by making surfaces that resist erosion and capture silt, and by promoting early lithification that helps delicate textures survive burial. Volcanic input, though, intermittent paints signals across basins that later correlators can follow. Hydrothermal seepage, though, localized seeds, metalliferous veneers that mark the youth of crust and the vigor of fluid flow at spreading centers. Through these means, the seafloor writes a measured narrative in layers that tally both the background rain and the bursts that break it, and in fabrics that echo the strength, direction, and duration of the currents and waves that shaped them. Shallow shelves 600 million years ago are broad sunlit platforms where clear water, gentle motion, and firm microbial carpets build low relief banks of carbonate sand and mud that shift slowly under tides and waves. A shelf is the underwater edge of a continent that slopes very gently from the shoreline toward deeper water and remains within the reach of ordinary storms. On these shelves, the seabed lies entirely inside the photic zone, the depth to which enough light penetrates to drive photosynthesis, so light-powered microbes coat grains, seal loose mud into skins, and trap passing silt into thin blankets that hold together under modest shear. The water is warm at low latitudes and seasonally warm at higher latitudes, and clarity is high where rivers supply little fine mud or where currents sweep fines away. Daily the tide raises and lowers water level, and pushes a steady current across banks and flats, and fair weather waves roll in as low swells that spend their energy in the outer meters above the bed, sorting grains by size and keeping the skin of the seabed in slow motion. During the rare, strong storm, deeper wave orbits reach down and rework the upper layers into broad hummocky sheets, but the ordinary condition is calm enough for subtle textures to survive between such events. Grain types reflect the chemistry of the water. Where saturation is high, tiny carbonate crystals precipitate directly from seawater onto grain surfaces. Ooids grow as rounded coated sand-sized particles when nuclei such as shell fragments, quartz specks or pellets roll under waves and tides and pick up concentric layers of carbonate. Peloids, which are small structureless carbonate pellets, form in places where microbial films break and roll into grains that later accrete micrete. Between these sand-sized fractions, micritic mud settles from suspension and accumulates in lee shadows of small bed forms and around the edges of mats that baffle flow. In zones of stronger motion, cross-bedded bars and ribbons of ooid sand climb and migrate along the direction of the dominant current, while in quieter belts, flat laminated mud with rare ripple trains blankets the floor. The distribution of these fabrics is tied to small changes in depth and to the layout of banks, passes and shoals. Slightly shallower crests host vigorous agitation that prevents mud from settling and favours the growth and accumulation of ooids, so shoal tops gleam as bright mobile sand. Margins a little deeper, where orbital speeds fall below the threshold for continuous transport, catch micrete between bursts of sand movement and build composite layers of thin mud drapes alternating with ripple and small dune sets, in still deeper reaches of the shelf beyond the fair weather wave base. But inside storm reach, thin beds of mud accumulate steadily and are punctuated by storm-generated sheets of coarser material that thin landward and seaward. Microbial mats strengthen the surface everywhere light and calm combine. A mat ground is a thin, cohesive surface formed by microbes that exude sticky substances. It traps silt that would otherwise be resuspended, reduces the erodibility of the bed, and records faint crinkle and wrinkle marks that align with the direction of the last flow. On tidal flats at the landward edge of the shelf, mats yield polygonal crack patterns when briefly exposed and then re-immersed, while in permanently submerged zones they fix the upper grains and encourage the growth of micritic cement that glues the carpet within the topmost finger breadth of sediment. This early lithification turns soft mud into a crust that resists scours from the next event and allows delicate textures to persist under later burial. Tidal processes imprint a predictable rhythm on these shelves. The rise and fall of water twice in a day, or once in a day depending on local resonance sets alternating flood and ebb currents through inlets and across open banks. Where channels connect interior lagoons to the open shelf, these currents build large subtidal dunes of ooid sand whose crests migrate and split as the dominant phase winds first one way and then the other across the spring to neap cycle. Elsewhere, where the tide runs as a broad sheet across low-relief sand ribbons align with flow and leave intervening strips of exposed mat and mud. The changing water level also regulates the time available for photosynthesis on very shallow banks with longer daily immersion, promoting continuous microbial growth and very brief exposure reducing it. Wave processes act with tides to set bed forms. Fair weather waves organize the sand into small oscillation ripples with symmetrical crests, where the back and forth motion dominates while steady tidal drift superposes a slight asymmetry as the net current adds a directional push. During storms, larger waves and storm-driven flows flatten small ripples into broader low hummocks, whose axes often trend with the direction of the main storm current. After calm returns, microbes recolonize the smoothed surfaces. Thin mud settles into lows, and a new generation of ripples climbs once agitation falls below the threshold. Chemical precipitation proceeds quietly throughout. Over the cleanest shoals where agitation and light are both strong carbonate can precipitate directly from seawater in the form of micrate clouds that later settle as thin lime mud drapes over ripples and matte skins. In the swales between dunes where flow slows but remains clear, tiny aragonite needles grow in place on trapped films and bind surrounding grains. Around small gas seeps or along subtle density steps, localized cementation can build hard grounds that show borings and incrustations even in this pre-burrowing world, with later erosion beveling their tops and leaving them as smooth, firm surfaces that accept the next thin blanket of sand. The water column above the shelf communicates with the open sea through passes whose depth and width control exchange. Where a sill is deep oceanic water with higher salinity or different temperature can flush the platform regularly, refreshing oxygen and resetting the density structure after stratifying spells. Where a sill is shallow, summer heating and evaporation can build a stable, slightly denser surface layer that recirculates within the platform until storm season returns, and winter cooling or rare cold nights can weaken that lid and allow brief overturns that restore homogeneity. In arid belts with wide shelves, high evaporation can push salinity high enough that precipitation of gypsum begins in isolated back barriers and ponds, while the open bank proper continues to build carbonate grains under clear water. In humid belts, floods from rivers deliver thin veils of mud that spread as buoyant plumes along coasts and settle slowly, where agitation wanes, temporarily dulling clarity and shifting oid growth toward offshore shoals until the flux subsides. The accumulations that result are organized into laterally extensive, vertically repetitive packages. At the smallest scale, laminae record daily and fortnightly cycles as thin mud drapes alternate with slightly coarser sets across spring and neap tides. At an intermediate scale, fair weather and storm alternations stack thin muds beneath occasional hummocky beds. At a larger scale, still slow shifts in relative sea level move facies belts landward or seaward, so that shoal-top ooid sands overlie or underlie quiet mid-shelf. Muds and tidal channel dunes cut down and fill during a phase of strong exchange before shoals migrate and seal their tops. Early cement glues parts of the stack soon after burial and protects delicate textures, while adjacent softer intervals compact and sharpen contrasts. Across the shelf, biology is present as mats and as the simple soft macroforms that rest on them, but here their mechanical expression is most evident. Mats baffle bind and stabilize grains so that the physical signature of tides and waves is preserved with exceptional clarity. The gentle repeating environment makes surfaces that are reworked often but not deeply, and each reworking produces a fresh template for the next round of coating, trapping and sorting. In this way, the shallow shelf becomes a factory for thin but widespread layers of carbonate sand and mud, organized by depth, energy and light into banks and flats that creep across the platform as water level and sediment supply change slowly. The record left behind is a quiet tapestry of ripples, cross sets, mud drapes, wrinkle marks and thin storm sheets, all held together by early cement along grains and by the resilient skins woven by microbial communities that thrive in clear, well-lit water. Coasts 600 million years ago form shifting boundaries, where river water meets the sea, where tides and waves rework the edge each day, and where broad deltas advance or retreat according to the balance between sediment supply and the quiet rise of the ocean surface. Low relief land and high sea level create long shallow gradients from inland basin to open shelf, so the shore is sinuous and sensitive, and its features migrate under modest changes in water level or sand transport. Rivers descend from subdued uplands and carry suspended silt and clay, along with sand that moves near the bed as pulses tied to seasonal rains, and to the occasional storm that sweeps slopes clean. At the mouth, the fresh plume spreads atop heavier seawater and slows, dropping coarser grains first as small mouth bars that split flow and seed shallow channels. The lighter plume continues as a surface lens that turns seaward under the push of river momentum and wind, while beneath it a denser counterflow creeps landward, a quiet estuarine circulation that exchanges salt and heat through the inlet. Tides entering from the open sea modulate this meeting. Twice in a day or once in a day, depending on basin geometry, water floods landward and ebbs seaward, setting currents that alternately strengthen and oppose the river jet. Where the tidal range is large relative to river discharge, the flood and ebb build broad channels, with banks of sand that climb and slip as crests migrate, and slack periods allow fine mud to settle in sheltered coves. Where river momentum dominates distributary channels, extend seaward break into smaller threads, and deliver sand to mouth bars that coalesce into shallow subdeltas. Waves arriving along the coast add a third control. Their oblique approach sets up a longshore drift that pushes foreshore sand down, coast smoothing irregularities and feeding spits that grow across inlets. During calm spells, small symmetrical ripples reform on beaches and tidal flats. During storms, larger breakers tear into the shore face suspend sand and drive it landward across low barriers as sheets that settle in quiet backwaters. Over years to centuries, this repeated overwash migrates barrier islands toward the mainland and builds washover fans that thin away from breaches while inlets open at weak spots during severe events and later close as drift resumes. In arid belts, evaporation outpaces inflow on the highest flats and salt crusts, and gypsum crystals grow in shallow ponds that flood during spring tides and dry under sun, creating hard, bright pavements that crack and reflood in a seasonal rhythm. In humid belts, floods deliver silt-laden plumes that spread across estuaries and coat intertidal benches, with thin, cohesive blankets dulling water clarity and briefly choking shoals before clearer months return. Microbial mats cover many exposed and gently submerged surfaces and act as quiet engineers. They weave sticky films across mud-trapped silt from turbid pulses and confer strength so that the next tide does not scour freshly laid laminae. On broad tidal flats, mats produce wrinkle marks that align with the last current and polygonal networks of shrinkage cracks where brief exposure allows drying. On subtidal benches, they stiffen skins that resist the first velocities of flood and ebb, and that foster early carbonate cement that turns soft mud into a fragile crust. Deltas differ in outline according to which agent leads. Where river supply is great and waves and tides are modest lobes push seaward with protruding tips, and a maze of shallow channels that avulse as mouth bars rise to the surface and divert flow sideways. Where waves are strong, distributary mouths are smoothed into a shoreline held near alignment by drift. The sand is reworked into strand planes, and the delta builds as a low, even arc that advances during intervals of high supply and retreats when supply wanes. Where tides are strong, channels widen and deepen into funnel-shaped mouths. Banks are scoured and armoured with sand dunes that reverse with flood and ebb, and sandy islands with elongate shapes align with the tidal current, their interiors floored by mud that settles during slack water. In all cases, the vertical build of a delta reflects repeated small steps rather than single leaps. Coarse sand tops bars and channel floors. Silt and clay settle from suspension on broad low back swamps and interdistributary bays during quiet phases, and storm or spring tide incursions lay down sheets that bridge marsh-free flats and tidal meadows of microbial origin. As relative sea level rises slowly, accommodation increases and allows thicker packages of mud to stack between sandy channel belts. As supply briefly outpaces rise, channels prograde mouth bars weld and shoreline steps seaward. The strength and timing of tide set the tidal prism the volume of water that must pass through an inlet during a cycle, and this prism controls channel cross-sections and the stability of openings. When the prism is large relative to littoral drift, inlets persist and even migrate along barriers as the balance of flood and ebb shifts. When the prism is small, longshore sand can close entrances unless storms reopen them. The interplay between inlet hydraulics and alongshore transport imprints rhythmic spacing on barrier chains and sets the pace at which back barrier basins fill or are flushed. Within estuaries, the vertical layering of fresh over salt thickens during calm weather and thins during wind events and spring tides that stir the column. Where stratification is strong, a sharp halocline traps fine particles in a turbidity maximum near the head of the salt wedge. Where stirring strengthens the wedge, collapses, and bottom oxygen increases. During cold spells, dense surface water forms and sinks along the floor, ventilating deep holes and scouring low sills. During warm spells, evaporation raises surface salinity in shallow ponds until brief overflows export dense brines back to channels, leaving thin halite skins to be broken by the next tide. Around river mouths during flood seasons, sediment concentrations peak, and watercolour shifts toward brown, but estuarine circulation still inserts seawater beneath the plume and mixes salt upward through interfacial waves and shear. That mixing together with wind-set currents spreads a lens of brackish water along the coast for many tens of kilometres, turning with the Coriolis tendency, according to hemisphere, and partially recirculating into adjacent bays. Morphology responds to storms without losing memory of calmer intervals. A severe cyclone or a train of winter storms can cut new inlets, flatten dunes, and strip the shore face to a depth reached by the largest waves, leaving behind a ravinement surface that truncates older beds. In the seasons that follow, fair weather waves rebuild bars and berms and tides, sort sands back into channels and shoals, while fines settle into protected pockets, and begin again the slow work of accretion under mats. Because relief is low, a small long-term rise in the mean level carries the shoreline far inland, translating the whole coastal system across the plain. At the same time, because sand moves readily along shore, the detailed planform changes as spits hook and hollow, as ebb deltas blossom at inlet mouths, and as flood tidal deltas spread fans landward. Through these motions, the coast remains a place of exchange rather than of storage. Only where channels abandon their courses and where lobes are left behind by avulsion does lasting land build, and even there quiet water turns that land into low islands, ringed by tidal creeks and floored by laminated mud. In arid shelves, salt-flat sequences accumulate with repeated cycles of inundation and desiccation, and in humid shelves thin coals are absent, because rooted vascular plants are not yet a coastal element, leaving the organic imprint as films within laminae and as early cements with distinctive carbon signatures along shallow reaction fronts. The long view sees the edge progressing in pulses set by climate, by sediment yield from the interior, and by the geometry of available space along the margin. With high sea level spaces ample, and the coast draws long arcs around embayments, and across the mouths of structural lows. With lower supply barriers thin, and retreat by overwash. With higher supply distributaries thicken and march outward between narrowing wave-built ribs. Each path leaves its texture cross-bedded channel sands with bidirectional sets where tides rule, evenly laminated strand-plane sheets where waves smooth the front, heterolithic rhythmite stacks where flood and ebb alternate mud and sand with seasonal fidelity. Microbial mats stabilize each surface long enough for the next tide to add a paper-thin coat, and the cumulative effect of countless such coats is a steady, quiet growth of the coastal wedge. In this time, the coast does not hold still, yet its rates are gentle and its rearrangements are measured in the widths of bars and the distances between inlets, rather than in sudden cliffs or steep deltas. The shore remains low, broad and luminous under long light, a band where river tide and wave continually trade grains, and where the position of the edge is the moving outcome of that trade. Soft-bodied communities spread across the seafloor 600 million years ago and occupy wide belts of shallow to middle-depth settings where firm microbial mats provide stable ground. A microbial mat is a thin, cohesive carpet built by microbes that exude sticky substances. It binds loose grains, traps silt, and creates a skin that resists small currents. On these firm grounds, large organisms with soft bodies arrange themselves in patches and sheets that show repeated shapes and orderly spacing. Many stand as fronds with quilt-like panels that branch in mirrored patterns. Others lie as low ovals or round discs pressed gently to the mat. Still others rise as lobed domes with faint radial seams. Holdfast discs anchor some forms to the carpet, while reclining fronds rest directly upon it. The seafloor around them bears wrinkle marks and small polygons where the mat tightens and relaxes under changing flow, and thin drapes of lime mud settle between events to seal each surface before the next wave or tide returns. Light penetrates through clear shelf water and supports high microbial productivity on the mats. Yet energy remains low enough that sand does not scour continuously, so bodies retain shape after death and can be preserved in place beneath the next skim of sediment. The water is oxygen-bearing near the floor where mixing is steady, though deeper basins beyond these grounds can trend oxygen poor. In the belts where soft-bodied communities thrive, gentle renewal by tides and fair weather waves thins the boundary layer around surfaces and sustains exchange across skins. Feeding strategies match these conditions. Many organisms present broad panels to the flow and rely on diffusion across their tissues and on slow boundary layer motion to trade dissolved substances with seawater. Diffusion is the natural spread of dissolved molecules from higher concentration to lower concentration. When a weak current slides over a frond, the near-surface film grows thinner and exchange improves. Communities often show alignment with the prevailing current, and individuals keep distances that limit wake interference, a spacing that arises from physics rather than from behavior. Some low forms create shallow pressure shadows on the mat that trap fine particles, and those lee pockets later host juveniles, suggesting that microtopography on the mat helps small bodies settle and survive. Body plans vary yet share soft partitions. Range-like fronds branch from a central rib into leaflets that split again in repeating sets, a pattern called fractal-like branching that packs surface area into a thin form. Disc-like organisms bear concentric ridges and radiating grooves, giving the appearance of rings and spokes across a panel that sits flush to the bed. Elongate fronds recline as ovals with gentle corrugations, and broad petal forms organize into rosettes. Some individuals show a narrow stalk that meets a small circular holdfast, a low puck that grips the mat. Others rise directly from the carpet with no obvious stem. Within a bed, sizes range from handspan juveniles to larger adults measured in tens of handspans, yet the outlines remain consistent, implying growth by the addition of modules or the inflation of existing panels, rather than by shedding hard parts. The lack of hard skeletons keeps communities quiet in life and in death. When burial arrives as a thin event layer, bodies collapse softly, and leave moulds that are later cast by new sediment or were coated early by mineral films preserving crisp relief against the flat of the mat. Energy setting sorts assemblages across depth. On shallower banks within fair weather wave, reach fronds lean with the current and align into ribbons parallel to flood and ebb. Storms that pass each season prune tall forms and favour low reclining ovals that resist shear. On mid-shelf flats below ordinary wave base but within storm influence, taller fronds and wide rosettes spread in even grids, and their holdfasts pucker the mat into small raised rings. In quiet embayments that face restricted exchange discs and lobed domes dominate, and fine drapes between generations are thicker. Where river plumes occasionally pass thin silty veneers, blanket a bed, and are then colonised again by mats and juveniles once clarity returns. The mat itself acts as engineer and archive. It stabilises the bed, encourages early micrite cement to grow along filaments and around grains, and limits sinking of bodies into soft mud. Wrinkle marks, shrinkage polygons, and small gas escape blisters record the state of the carpet before burial. Because deep churning by animals is not yet a pervasive process in these grounds, surfaces remain intact between events, and delicate details persist from one tide to the next. Growth patterns appear as cohorts. Many bedding planes hold numerous small individuals clustered around larger ones, and size frequency spreads smoothly rather than in jumps consistent with steady settlement of microscopic propagules from the water and with local clonal budding on the mat. Propagules are small reproductive units that settle, attach, and grow. The presence of aligned triplets and chains along frond margins suggests that some forms bud by splitting a panel and inflating a copy beside the parent. The evenness of sizes on single surfaces implies that burial captures a living neighbourhood at a moment rather than a time-averaged layer. Food webs remain simple. Bite marks and through borings on preserved bodies are scarce, and edges remain intact, pointing to low levels of macroscale predation. Microscopic grazing of the mat likely occurs, yet leaves only subtle film damage rather than widespread disruption. The water above carries dissolved and fine particulate organic matter from microbial production on the mat and from distant sources delivered by gentle currents, and broad panels harvest that flux by diffusion and by slow advection. In many places, the community builds atop carbonate sand and micrite produced in place on the shelf, and early cement binds a thin composite pavement that resists the next event's shear. Environmental limits bound the belt of life. Where waves grow too strong, rolling sand abrades the mat and dislodges forms. Where river delivery of silt stays high for long stretches repeated, smothering reduces open mat and limits settlement. Where stratification strengthens and near-bottom oxygen falls for long periods, communities fade. The best grounds sit on stable, gently agitated flats, with clear water, frequent yet not destructive stirring and steady renewal of near-bed flow. Geography of the time supplies many such places because sea level is high, shelves are broad and low gradients spread suitable depths far from shore. Taxonomic relations remain uncertain because soft parts provide few diagnostic details, and the preserved record is largely surface moulds and casts. Some shapes may lie near the base of later animal groups, others may represent separate branches with no later analogues, and some may be large integrated consortia of cells organized on a mat. What is secure is the physical and chemical frame of their success firm, unchurned beds, gentle currents that thin boundary layers, oxygen present near the floor, clear light and thin events that bury without scour so that neighbourhoods are sealed in place. Over time, repeated burial and recolonization build a stack of surfaces, each carrying a living tableau at the moment of cover. Between surfaces, thin drapes of carbonate mud and very fine sand record calm intervals. Where storms pass, a low hummocky sheet caps a bed and is followed by a return to even spacing as juveniles settle again. The cumulative result is a calm archive of soft bodies on stiff mats preserved with unusual clarity. In this quiet world, broad panels breathe with the passing flow, hold-fast discs grip the living carpet and rosettes, and domes share space in orderly arrays that follow depth and energy, like contour lines on a map drawn by water and light. The first subtle motions within the seabed appear 600 million years ago, as small animals begin to push into across and just below firm microbial mats, leaving faint trails, shallow grooves and short burrows that mark a shift from surfaces ruled by carpets to surfaces that are gently worked from within. A burrow is a void or fill made by an organism moving through sediment. Bioturbation is the mixing of sediment by living things. In this interval, the activity is modest in depth and scale. Yet its presence matters because even millimetre to centimetre motions alter the skin of the seabed change. How water and dissolved substances pass between pore space and the overlying flow, and introduce irregular fabrics that break the continuous sheen of mat grounds. The organisms responsible are small, soft-bodied forms that live at the interface between water and sediment. They enter the mat along tiny openings, creep through the uppermost layer, and either leave an open tube for a short time or backfill the space with compacted grains. The paths they cut are simple and sinuous rather than highly branched, and they commonly track along planes parallel to the surface rather than plunging deeply. Vertical movement rarely reaches beyond a few finger breadths, and most activity hugs the topmost centimetres, where oxygen from the water can still diffuse inward. These constraints match the physics and chemistry of the bed. Oxygen penetrates only a short distance into undisturbed mud beneath a mat because microbes consume it. A small increase in oxygen at the water-sediment boundary, or a moment of stronger mixing thins that consumption zone, and opens a narrow band in which animals can work without entering sulfide-rich layers that are hostile to soft tissues. Pulses of oxygen arrive when tides run faster, when fair weather waves pass, or when cool, denser nearshore water spreads across flats after nightfall or after a storm. In those windows, small bilaterian animals move. Their bodies elongate and contract, or waves of muscle pass along them in peristaltic strokes that push grains aside and pull bodies forward. Many secrete mucus that lines the path and reduces friction, and that lining remains as a film which later binds fine particles and strengthens the trace against collapse. Some animals anchor intermittently and pull, leaving short straight shafts that stop suddenly where oxygen drops. Others graze across the mat surface and scrape or rasp the film, gently leaving cross-hatched or meandering surface traces that cut the upper fraction of a grain's depth, and then heal as microbes regrow and thin carbonate settles. Where motion remains inside the top layer, the fill records meniscate structures, small crescent-shaped packets of backfill laid down, as the animal packs grains behind itself. Where motion pierces the mat and re-enters it nearby, paired apertures mark the start and end of a brief foray that resets the skin locally. The distribution of traces follows energy belts and oxygen patterns set by physical processes already in place. On very shallow shoals where agitation is continuous, sand rolls too often for sustained infaunal work and traces are sparse and quickly erased. On mid-shelf flats within fair weather wave reach, but below constant scouring narrow horizontal trails are common, and thread between the holdfasts and fronds of soft-bodied communities that remain on the map. In more protected embayments where stratification sometimes lowers near bottom, oxygen traces cluster on surfaces that coincide with brief ventilated episodes, and then fade in intervals when the chemocline lies close to the bed. Along tidal inlets, compacted sinuous tubes climb gentle slopes between ripple troughs, showing that flood and ebb steer activity windows, and that animals exploit slack periods to move and feed before currents strengthen again. The interplay with microbial mats is evident on every worked surface. Mats resist penetration and hold together under minor shear, but once an animal opens a seam, water and oxygen can enter the pore space more easily, and a ribbon of altered chemistry blooms along the path. Iron oxides may precipitate where oxygen meets reduced iron in pore waters and stain the linings rusty. Where sulfate reduction remains active just below pyrite, may accumulate along the lower margins of the trace and fix a thin dark seam that outlines the root under a microscope. These chemical halos stabilize the burrow and increase its chance of survival during later burial. At the same time, the mechanical consequence of mixing appears as disrupted laminae. Wrinkle marks continue across a plane until they reach a backfilled tube where they bend or stop, and thin mud drapes that would otherwise lie flat now part around a meniscate packet. Over time, the sum of many such microdisturbances roughens the bed at scales that matter for flow across the surface. Boundary layers thin or thicken locally, depending on the small relief and exchange across the interface becomes patchier. Fecal pellets accumulate as strings of rounded grains pressed together by the animal's gut and expelled into open water or into the burrow itself. These pellets resist compaction slightly better than surrounding mud, and they build faint pellet-rich laminae in quiet spots, or line the floors of shallow tubes in more agitated belts. Some animals adopt a sit-and-wait posture in tiny vertical shafts that widen toward the top like trumpet mouths. Others build U-shaped passages with openings a palm apart, allowing water to flush the tube during each tidal swing. Even these simplest architectures imply a body plan with a head and tail, a front and back, and the ability to coordinate motion traits that align with bilaterian organization, though taxonomy remains uncertain from traces alone. Preservation favors moments of quick cover. A thin event layer of fine silt or lime mud settles from a storm-waning stage, or from a turbid river plume blankets the surface and flows into shallow depressions over open apertures. Soft bodies decay soon after, but the filled tubes remain as subtle contrasts in compaction and cement. Where early carbonate precipitates along the mucus film, a delicate lining survives and stiffens the void. Where mats recover quickly after burial, a new film grows across the top and seals the layer protecting the cast beneath. Repetition builds a stack of worked and unworked horizons, each separated by thin event sheets or fair weather veneers. The proportion of worked surfaces to untouched backgrounds varies through space and time in step with oxygen energy and sedimentation rate. On banks with frequent gentle stirring and clear water, worked intervals become more common. In deeper, more isolated arms, long stretches of pure background separate, sparse worked layers that align with isolated ventilated phases. The net effect on the seabed's function is measurable. Even shallow mixing softens sharp redox boundaries, allows oxidants to reach a little deeper, encourages reoxidation of reduced iron and sulfur near the surface, and releases dissolved nutrients that have been locked in anoxic pore waters back to the water column. Permeability rises along burrow networks so small, pressure changes from waves and tides pump water in and out of the bed more effectively, a process called bioirrigation that enhances exchange despite the small size of individual traces. Each short tube acts as a nozzle that focuses flow during pressure swings, and the collective action of many such nozzles produces a subtle but persistent ventilation of the uppermost layer. Surface fabrics respond in turn. Mats continue to weave skins and to trap fines, but their continuity is broken more often, and microtopography shows a mix of ripple trains, wrinkle fields, and gently pitted textures where burrow mouths stood. Soft body communities still occupy broad belts, yet at their margins and between their patches the sediment is now lightly churned, and bed forms carry the overprint of life as well as water. The world remains quiet and firm relative to later times, with no deep galleries or intense bulldozing of the column, but the change is real. The skin of the seabed shifts from a near-continuous carpet that locks grains where they fall to a lightly worked fabric, in which small animals move, feed and breathe within the topmost centimetres. Their traces lace the mat with airways, their pellets seed thin laminae, and their shallow excavation introduces a new texture to the archive. In this way, the earliest infaunal motion begins not as a sudden upheaval, but as a faint repeating disturbance that spreads across suitable grounds, whenever oxygen allows and energy is gentle, a first delicate mixing that marks the start of life, reshaping the very surface it inhabits. Minerals at the smallest scales fix the conditions of 600 million years ago into durable signals so that grains, cements, and microscopic textures store the chemistry of water, the flow of pore fluids, and the presence or absence of oxygen within the seabed. Pyrite forms where sulfate reduction supplies sulfide, and where dissolved iron is available, and it often grows as framboids, which are tiny spheres built from clusters of even tinier crystals. The size and spread of framboids reflect how long sulfide persists in pore waters and how close the redox boundary lies to the surface, where oxygen penetrates only a finger's depth, and sulfate reduction is strong, small, narrowly distributed framboids grow quickly and pack into laminae, where the water above is well ventilated and pore waters turn sulfidic only deeper. Down larger, more varied framboids appear and are scattered rather than concentrated. In the same horizons, iron oxides coat grains where small pulses of oxygen from tides and waves enter the bed. At the sharp meeting of oxygen and sulfide, these coatings are stripped, leaving a crisp colour break. Carbonate cements nucleate early around grains along microbial filaments, and on the walls of tiny voids turning soft fabrics into firm rock within seasons to years. Aragonite and high magnesium calcite, the common early forms in this seawater, grow as fibrous and bladed crystals that rim ooids and bind peloids. Later, as burial proceeds and waters warm, some of these early cements recrystallize into low magnesium calcite while preserving ghostly outlines of the original needles. Dolomite or calcium magnesium carbonate appears where magnesium-rich fluids linger and react with macritic muds. Its crystals are often saddle-shaped at larger scales, but in these early replacements the crystals are tiny and planar, advancing through mud in fronts that respect lamination. Dolomitization is the replacement of original carbonate by dolomite through exchange with magnesium-rich water, and it records pathways of fluid flow along beds and through subtle pressure gradients. Ooids store microhistory in their cortices. Each concentric layer reflects a time of motion and of supersaturated water, and under magnification the cortex shows radial crystals that grew outward during rolling on shoals, and tangential laminae built by micrite that wrapped a quieting surface. Breaks, pits, and dark seams inside a cortex mark. Brief pauses, slight dissolution in undersaturated water, or the passage of pore fluids that carry different chemistry than the seawater of growth. Peloid structureless grains made from aggregated carbonate mud hide delicate filaments that show where microbes bound the mud before pellets were rolled and rounded. Early rims line their borders and test the timing of cement relative to burial. In muds, A lattice of tiny calcite crystals nucleates on organic films and on clay surfaces, and these microcrystals coalesce into micrite that fills spaces between larger grains. The clays themselves transform as burial warms them. Smectite, a swelling clay, loses interlayer water and exchanges cations to become elite and non-swelling clay in a process called elitization that releases potassium and changes the ease with which pore fluids move. The ratio of elite to smectite thus tracks the progress of burial and the passage of time at low temperatures rather than sudden heating. Where ash layers lie within the stack volcanic glass hydrates and alters to clay minerals and zeolites, creating pale seams of orthogenic crystals that grow from solution inside pores. Orthogenic means grown in place within the sediment after deposition. In those seams, delicate shards line up and preserve the settling fabric of the original ash, while their composition records the composition of fluids that did the altering. Early diagenetic carbonate precipitated from pore waters during the decay of organic matter bears carbon isotopic values that are lighter than the overlying marine cements. Isotopes are atoms of the same element with different mass. The ratio of light to heavy isotopes in a mineral reflects the pool from which it grew. Pore water carbonate that drew carbon from methane oxidation or from organic decay shows this light signature, while seawater cements record the average marine value set by the global carbon cycle at the time. Where these two types of carbonate interleave their contrasting values, bind together a vertical record of pore processes and open water chemistry. Sulfur isotopes in pyrite carry the imprint of sulfate reduction, with fractionations that depend on the availability of sulfate and on the rate of reduction. In this era, rising but not modern, sulfate yields fractionations that can be large in restricted settings and smaller where supply is steady and layered. Pyrite can capture both. Oxygen isotopes in carbonate respond to the temperature and isotopic composition of the water from which they precipitated. Early cements thus hold a near-surface temperature signal, while later burial cements reflect warmer fluids at depth. Fluid inclusions contribute a direct sample of ancient water. A fluid inclusion is a microscopic pocket of liquid trapped within a growing crystal. As carbonate cements grow across a pore, tiny volumes of pore water become sealed inside. When these inclusions remain intact, their salinities, and if carefully studied, their dissolved gases can report the character of the fluid at the moment of trapping. On evaporative flats and in restricted lagoons, inclusions in early gypsum or in early carbonate reveal higher salinity. On open banks they show values near normal seawater. In many beds, radiating fans of vesicular aragonite or whiskery calcite sprout from matte surfaces beneath thinner vent layers, a texture called shrub or spherulitic cement that forms when pore waters become briefly oversaturated after rapid burial of reactive surfaces. These shrubs stiffen the layer and capture the delicate impressions of fronds and discs in the lamina just above. Where gas bubbles rose from shallow methanogenesis, small escape structures break mats and create domes rimmed by cement that later hardens into blister-like features. The iron and manganese cycles leave their own micronotes. Manganese oxides deposit as black dendritic films along fractures and on the surfaces of early cements where oxidizing water moved, and iron oxides coat grains with red to brown skins that thin and thicken across a lamina according to small shifts in oxygen supply. At boundaries where oxygenated event layers cap anoxic mud, a colour front pins to the contact and moves slowly downward as diffusion and reaction proceed. The distance of that front from the surface in buried pairs of beds calibrates how quickly oxic pulses penetrated. Even pores remember flow. In cross-section, meniscate fills of shallow burrows appear, as repeating curved packets separated by thin clay or micrite partings, and these packets differ slightly in cement abundance from the surrounding mud because mucus and pellet coatings change nucleation. Where tubes were open, briefly, geopital fabrics form as carbonate mud settles within cavities and shows which way was up at the time of filling. Later cements occupy the remaining space and record a second phase of water movement with different composition. In sand's pressure solution at grain contacts produces styler lights, serrated dissolution seams that cut through carbonate packs and remove small volumes of material. The amplitude and spacing of these seams measure how much overburden has worked on the bed and how much material has passed into solution and later precipitated nearby. Trace metals ride the redox boundary and fix into specific minerals. Under sulfidic pore waters, copper and zinc join iron sulfides and form minor phases that concentrate at the chemocline. Under ferruginous conditions, rare earth elements adsorb to iron oxides that line the topmost millimeters of beds. These tiny enrichments provide fingerprints of water column state above and of pore water paths below. Taken together, the small archive reads like a ledger. Framboid sizes sketch oxygen access and the depth of the redox cline. Early cement fabrics register agitation clarity and the degree of saturation on the bed. Dolomite patches map magnesium-rich pathways through mud. Clay transformations tally burial and time at low heat. Isotopes in carbon, oxygen, and sulfur separate open water signals from pore water signals and mark short episodes of restriction, cooling, warming, or unusual carbon loading. Inclusions hold a drop of the ancient fluid and dendritic oxides, dissolving seams and geopetal fills plot the steps by which water and solids rearranged after grains settled. None of these notes stands alone, yet their convergence fixes specific conditions within narrow bounds. A thin sheet of micrite over ooid cross sets with small uniform framboids and fibrous aragonite rims tells of rapid burial on a ventilated bank with strong sulfate reduction just below. A mud lamina with larger varied framboids scattered dolomite rhombs and manganese dendrites along a parting speaks of slower burial intermittent oxidation and a pulse of more saline pore water. Such sentences written in crystals and coatings make the quiet details of this world recoverable, long after water and mats have gone. The minerals do not generalize, they register exactly where and how they formed, and in doing so they hold the finest scale of the story in place within the rock.